Hello everyone, welcome to this brand new series on LangChain, the framework that's changing how we build intelligent, context-aware applications using large language models. If you have ever wondered how chatbots, AI agents, or retrieval-based systems actually work behind the scenes, you're in the right place. In this series, we'll go beyond just theory. We'll build real-world LangChain project step by step, from simple conversational bots to AI systems that can use tools, reason with data, and even connect with external APIs and databases. By the end, you'll have the skills to design your own AI assistant or integrate LLMs into your apps confidently. But before we dive in, let's understand what LangChain really is. LangChain is a framework that bridges LLMs with real data and real tasks. It helps developers manage prompts, memory, retrievals, agents, and chains, all in a structured modular way. Think of it as a toolbox that turns a large language model into a powerful, goal-oriented system. In the upcoming videos, we'll explore LangChain concepts like chain, agents, retrieval and vector stores, and much more. Each topic will include hands-on coding demos and project-based learning. So, if you're excited to build real AI apps with LangChain, make sure to subscribe, hit the bell icon, and follow the series from the start. Let's unlock the true potential of language models together. I'm Abhishek, and this is the LangChain series. Let's get started. So in this video, we're going to have our first interaction with an LLM. So for that, first of all, I'd like to create a virtual environment. So open a terminal in VS Code. I've opened a folder in VS Code and then open a terminal. So we'll create our virtual environment, virtual env, venv. And I'm going to activate this virtual environment and install my libraries inside this. Okay, so the virtual environment is created, and now I'm going to install some libraries here. So pip install LangChain _ Google _ Chain AI, and I'll also install LangChain _ community, and let's also have Python .env or .env. So let's install these three libraries. And while this is being installed, I'm also going to create a requirements file, requirements.txt, and then mention these three libraries name here. So the first name is LangChain _ community. Second is LangChain _ Google _ Chain AI. Well, you might be wondering why we're installing Google Gen AI, because the Google Gen AI models, or like the Gemini models, are kind of free. The Flash models are free, so we will be using those models for our LLM interaction. I'm also going to create a .env file here, .env file, and inside this file we'll have our Gemini API key, which will be defined as Google _ API _ key, and then you can paste your Google API key in this place here. So paste your key. I'm going to replace my key here when I'm going to run the application here. Okay, so for the first program, or for the first interaction, we're going to create a Py file, but I would like to organize everything inside this single folder only for the future videos too. So let's just create a new folder and then type LLM interaction. And then inside this, I am going to create a file called chat model _ Gemini.py. Okay, so we are inside our Py file, and then this will be our first Python program, which will also be our first program to interact with Gemini model. So for that, I'm going to use the LangChain ecosystem. As you know that this is a series of LangChain. So we will import some libraries from LangChain _ Google _ Chain AI, import chat Google generative AI, and then another library is from .env, import load.env. So I'm going to call this function load.env. This is going to load our Google API key from the .env file. Then I'm going to define my model. My model, as I said, will be a Gemini model. So for that, I'm going to use a Gemini 2.5 Flash model today. And let's also invoke our model here. So model.invoke, let's provide a prompt, or like we can define a prompt here in string. So I'll say, what is the capital city of USA? And then I'm going to invoke my model with this prompt here. Let's save this in result. The model output will be saved in the result, and then I want to print out the result here. So let me clear this. So now if I run my application here, I can directly run my Python file from this button here. So run Python file, it activates my virtual environment, and then the Python file is being run, and you can see my result here. But we don't only get the result, but we get a lot of things inside this. We get the answers. We also get some metadata from the response, the number of tokens, and then stuff like that. What we only want here is our content part. So I'm going to hit result content. I'm going to clear this again and then run it. And we can see our result here. The capital city of USA is Washington, DC. Well, this is our very first interaction with a LLM here. So throughout the course of this video, we're going to use Gemini models as well as some Hugging Face models wherever applicable. We saw our very first interaction with an LLM, but I'll show you one problem that this LLM call has. So let me run this again. Or like, let me run this again. We got the answer, but I'm going to change the prompt here. So hello, my name is Abhishek. What is your name? So if I run this, it gives me an output. So I'm a large language model, an AI. I don't have a personal name like human does. You can just call me AI assistant if you like. And then in the initials of this message, it's written, hello Abhishek, how can I help you today? So now if I type, do you remember my name? And then run this, we'll see the problem here. As an AI, I don't have memory of past conversation or personal information about you. So no, I don't remember your name. So each and every LLM calls that we make are actually independent here. So how do we maintain these multi-turn conversations, meaning the contextual conversation like we have in this ChatGPT or like Gemini models? So we'll try to implement that here. So for that, I'm going to create a new folder called Chatbots. And inside this, I'm going to create a new file, chatbot.py. So let me install a LangChain core if I haven't done it. So pip install LangChain _core. Okay, I've already installed this. I can also mention this in the requirement, LangChain _core. So here I'm first going to import my Gemini model, import chat Google generative model, and then from LangChain core.messages, I'm going to import system message, human message, and AI message. So in this chatbot, we'll try to maintain that contextual information so that the AI remembers our name. So from .env import load.env. Okay, I'm going to load my credentials here. Then I'm going to define my model, which will be chat Google generative AI. The model name is going to be Gemini 2.5 Flash model. Now for the first message, I will now define a chat history here, which will be a list. And inside this, I'm first going to provide a system message. And the system message is going to say that you are a helpful AI assistant. Okay, so I'll keep this in loop so that I can continue talking with the bot. So I'm going to create a variable for user to type their message. So this is where user will be typing the message. And then whatever message the user types, I'm going to append this in my chat history. So that the chat history list will have the information about what the conversation is being happening. Equals to user input. Now I also need a break from this chat, a way to break this chat. So user input dot lower equals to exit. If the user types exit, I'm going to break this, or else I'm going to just invoke the model using my chat history. I'm not just going to provide a single prompt to the user, but I'm going to provide the model the entire contextual history of our conversation. Then the model is also going to reply back here. So that will also be appended. So chat history dot append, and then it will be appended as an AI message, where the content is going to be result dot content. Okay, and I'm also going to print my bot response here. So result dot content. Finally, once the conversation breaks out, I'm going to print the entire chat history. We had chat underscore history. Now, if we run this, we'll see that because of this particular list here, where we have stored everything or every conversation that we had throughout this loop, the model will be able to have some contextual information and at least remember our name, or at least remember what we've talked about in the past. So let me clear this output and then run this again. Save this and run this again. Do I have any errors? Yeah. So there's a comma missing here. Chat history. Okay, so run it. So it's asking for my message. I'm going to say, hello, my name is Abhishek. What is your name? Oh, okay. So I probably gave the wrong model name here. Okay. So I made a mistake here. So let me clear this again. I'm going to recorrect this. Gemini dash 2.5 dash flash is the correct model name. So let me run this again. Okay, so hello, I'm Abhishek. What is the name? So the model says, hello Abhishek, I do not have a name. I'm a large language model trained by Google. So let me also ask a few more questions. What are you trained on? So I've been trained by Google on a massive data set of text and code. This data set includes a wide variety of information from the internet and stuff like that. So I'm going to ask another question. What is the capital of India? So the capital of India is New Delhi. Now we'll check if the bot remembers our name or not. Do you remember my name? And yes, it does remember my name, because why it remembers our name is if we hit exit and then see our entire chat history, we can see that our entire chat history is being saved here. So this was the first message that we gave to the AI assistant. I asked this question. The AI replied me with this answer. I again asked another question using a human message, and then just because of the existence of this contextual information, the bot was able to remember what the conversation was about, or like was able to remember the stuff that we said in the past. So in the last video, we saw how we can include contextual information in our chatbot. So in this video, we're going to talk about something. We know what simple prompts are. We've already given prompts to our chatbot. But in this video, we're going to introduce a concept called ChatPromptTemplate. So ChatPromptTemplate in LangChain, it is a tool that helps you design and organize prompt for chat-based AI models in a structured way. So instead of writing the entire message each time, you can actually give a pattern that includes different roles like system, human, and AI, along with placeholders for dynamic values. So such placeholders are actually later filled with real data when the prompt is actually used. So what this does is it makes it easier to maintain, reuse, and modify prompts without changing the main logic of your application. So if I say it in simple terms, it's like creating a reusable message template that guides how our chatbot or AI assistant should behave and respond in a conversation. So I'm going to include my chat prompt template in my next program. So I'm going to create a new file here, 2.chatprompttemplate.py. So have our import LangChain _ core.prompts import chat prompt template. I'll have my model 2 LangChain _ Google Gen AI import chat Google generative AI, and I'll also have my messages here. So from LangChain, I'm not sure if I'll use this or not, but we'll keep it for now. Messages, import system message, human message, and AI message. Okay, first of all, what we're going to do is I might not invoke the model at all. I'm just going to show you how our prompts are created during chat prompt template. Okay, so this is actually chat prompt template, not chat message prompt template. So I'm first going to create a template here. So chat template equals to chat prompt template. I'm going to create a list inside this, and then for our system message, I'm going to type in this part, and then you are a helpful domain expert. So the domain is going to be a placeholder which will be filled later on whenever we execute this chat prompt template. And for the human message, I'm going to type explain in simple terms the concept of topic, and then the topic is also going to be our placeholder here. So whenever I create a prompt, what I'm going to do is I'm going to use my chat template dot invoke, and inside this, since we have two different placeholders here, so I'm going to provide the value of those placeholders. The first one is domain, so we'll call this quantum mechanics or quantum physics or something like that. And then the next is our topic, so I'm keeping the topic as wormhole. Okay, now if I try and print this prompt, what I'm going to see is a generated prompt from this chat prompt template here, where we have these two messages along with their placeholders. So let me clear this and then run this again. So if I run this, I can see my prompts here. So the first one is a system message. You are a helpful quantum physics expert, because the placeholder is being filled here. And then the human message, explain in simple terms the concept of wormhole. So if I need to invoke this, I can directly define my model here. So if you define a model, then you can directly invoke your model using this prompt here. So model.invoke and then prompt. I think you can do this by yourself and then check out the result here. What I wanted to show you in this video is a new style of generating our prompts using this chat prompt template. When building a chatbot, one of the biggest challenges is making it remember the conversation. You don't want to treat AI, or you don't want the AI to treat every user message as a brand new question. So that is where the message placeholder comes in. It's like a dynamic container for our chat history. Instead of manually combining all previous messages into a single string every time you generate a prompt, you just put a placeholder in your template and LangChain fills it automatically with the actual conversation that happened so far. So the placeholder doesn't just dump text, it preserves the role of each message, whether it came from the human, the AI, or the system. So this means that the AI can actually identify between instructions, user prompts, and its own past responses. So that is what allows multi-turn conversations to feel natural, that we see in ChatGPT or Gemini interfaces that we use. So another powerful aspect of such is reusability. So you can define a single chat template with a message placeholder, and it works for any number of previous conversations that we had. So whether the conversation has 2 turns or 20 turns, the placeholder always inserts the right history in the right format. So this also keeps the template clean, and you don't need complex logic to actually stitch the chat together or like put the chat together. So finally, message placeholders work seamlessly with LangChain's role-based messages like system message, human message, and AI message that we've already seen. So this combination actually ensures that our prompts are structured, clear, and also are context aware, which is actually essential when using LLMs for chatbot or customer support agents. So message placeholder is what lets a chatbot remember, understand roles, and continue conversations smoothly without you manually managing every previous line of dialogue. So that is what we're going to do in our upcoming code. So I'm going to create a new file called MessagePlaceHolder.py. What I'm also going to do is create a new file that actually contains or saves my conversation here. So let me write it at chatbot history .txt. As I told you that whenever we save our conversation, we save it in such a way that that the information of the message is being preserved. So I'll put a few messages here. So the first one is a human message where it says that I want to request a refund for my order, and the AI message says this thing. So okay, I will use this, and what I'm going to do is in my message placeholder, I am going to load this chat and then create a new prompt based on my new user input. So first of all, I'm just going to use from LangChain core.prompts import. The first one is going to be ChatPromptTemplate. This should be prompts. So ChatPromptTemplate, and then the other is going to be a message placeholder. So our chat template is going to be something that we've already seen. So chat template equals to chat prompt template. So this will contain a system message which says you are a very helpful customer support agent. and then I'll also load our conversation history that we already have in this file. So for that, I'm going to define a message placeholder with a variable name, and then the variable name is going to be like chat history. It's just a variable name. It does not need to match with the file name provided here. And then the third is going to be a human message, a new human message that will come in this particular place here. So I'll also indicate this as a string. Okay, so this is our chat template. Now I'm going to load a chat history from a file. So for that, I will create a list called chat history. So with open chat underscore history.txt as file, I can load our chat history dot extend file dot read lines. Okay. Now I will create my new prompt here based on the chat template that I have, as well as the chat history that I just loaded. So inside my chat history variable is going to be my chat history list, chat underscore history list. Okay, so this should be inside curly braces. So chat history list and chat history. Along with this, I'm going to also have a query, because the query also contains a placeholder here. So in the query, I'll ask where is my refund. So I can invoke this using a model too, but I just want to show you the use of placeholder here. So I'm just going to print my prompt or my new prompt here. Okay, so let me rerun this, and then we can see something's not right. Okay, so this should be txt. Clear this again and then run it. I definitely made some mistake here. Oh, it should be chatbot history, not chat history. Chatbot history. Okay, if I load this again, then we can see that the first message is a human message. You are a very helpful customer support agent. So far, we've focused on making AI conversations more natural and context aware. So we looked at how the AI can remember previous messages using features like MessagePlaceHolder, which allowed our chatbots to maintain multi-turn conversations like ChatGPT or Gemini. Back then, the AI could generate responses freely, which worked well for casual conversation. But the outputs were often unstructured, sometimes too long, inconsistent, or sometimes hard to process automatically. Now we're moving into the next step, which is structured responses. So instead of letting the AI respond however it wants, we want to define a schema that specifies the exact fields and types of information we want in the response. So this actually guides the AI to produce outputs that are predictable, organized, and easy to work with. So for example, we can ask it to summarize the review and identify the sentiment, and it will return the information in a clean and structured format. So the key idea is that structured output turns the AI from just a conversational partner into a reliable data source. So it complements the whatever we've done before. The AI still remembers the context of the conversation, but now its responses are also consistent and more readable, making it much easier to integrate into applications, dashboard, or any system that needs such actionable data. So let me jump to the code and then show you what I mean by that concept here. So I'm going to create a new folder here, which is going to be structured outputs. Let me give this as number 3. So inside this, I'm going to create a new file. and then the file name is going to be structuredoutput.py. So here again we're going to be using the Gemini model from Google. So import chat Google generative model. I'm also going to load my credentials. So .env import load.env, and here I'm going to introduce something new, which is a typed dict data type. So I'm going to load my credential, define my model, which is going to be a Gemini Flash model. So as I said, we want a proper structured output, right? So for that, we're going to define a schema. Let's write review. And the type is going to be typed dict. What we want is a summary, which is going to be in string, and a sentiment value, which is going to be also be in a string. So it can be a positive, negative, or sentiments like that. So now what I'm going to do is, instead of directly invoking the model, I'm going to convert this model output into a structured model output. So structured model equals to model dot with structured output, and then I'm going to provide my review class here. So what this does is, whenever this model is invoked, it tries to base its output on this particular structure provided here. Okay, so let me define my prompt. I'm not going to use a prompt chat prompt template. You know how to use that. So I'm just going to give my prompt here in a simple approach. So let's say this hardware is great, but the software feels kind of bloated. So many boilerplate apps, and my phone keeps hanging when I play PUBG. Okay, so this is going to be my review, and then based on this, I'm going to invoke my model with a structured model dot invoke, and then provide my prompt here, and then I'm going to print my response. So now if I try to run this, let me run this. So what I'm going to see is, I'm going to see a structured model output in this. So as I said, we gave the model a schema to base its response upon, and then the response is just based on the schema here. We have a sentiment, and then the summary. So the sentiment is negative, and then the summary is just hardware is great, but software is bloated with boilerplate codes, and the phone hangs when playing PUBG. So it is just trying to summarize this particular provided review prompt here, and then the response is quite well structured. Well, if I try to do something like this, so if I give a new prompt, and then okay, I'll also show you what happens if we don't provide such structured outputs here. So my prompt is going to be generate sentiment and summary of the review below. Review given. The review is, so if I paste my review here, or I can just do this, I can hit new prompt and then use this as f string, and then include my review using this prompt placeholder. Well, if I invoke this with not my structured model, but with my model, then I'm going to see that my response is going to be very much unstructured, which I don't actually want. So I'm not going to print this for now. Let's not print this. We'll just print it with the previous approach that we've done. Okay, something's wrong. I'm not sure what. So let me check again. Okay, we've not used the function invoke here. So let me write invoke, clear this, and run this again. I've not printed by result, in fact. So let me print by result too. So as you can see, the response is quite mixed. It says, here's the sentiment and summary of the review. Sentiment mixed to negative, positive, the hardware is slightly highly praised, and then yes, stuff like that, which is not actually structured. So we can actually base our LLM output response and then ask it to base it on the provided schema here. We can also include the details of such schema, but we'll do that in our upcoming video. In our previous video, we explored structured outputs, where the AI was guided to return information in a specific format like a summary and sentiment. That approach made the AI's response predictable and easy to use, but it was relatively simple. We were mostly extracting a summary and a single sentiment value. So in this next step, we're taking structured output to the next level by introducing rich schemas with multiple fields, annotation, and optional elements. Now, instead of just a summary, we can ask the AI to extract multiple layers of information from a single piece of text. The key themes that is talked about, a concise summary, overall sentiment, and even detailed pros and cons. We're also telling the AI exactly how each field should be formatted and making it strict so it follows to the schema precisely. So this approach transforms the AI into a powerful data extractor. You can feed it complex reviews, articles, or even long form text, and it will actually return you a structured, machine readable object that you can directly use in dashboards, analytical tools, or even databases. So the AI is no longer just answering your questions or chatting. Now it's systematically organizing knowledge in a way that applications can consume automatically. So by building on what we learned about contextual and structured output, the following implementation will show you how to scale from simple structured output to detailed multi-field extraction, making AI truly practical for real-world tasks like review analysis, product insights, or content summarization. So let's go for the code now. Okay, I'm going to create a new file inside this, detailed output structured.py. I'm going to use these same fields, the same model that I have here. I'll just paste this, but what I'm going to do is I'm going to add a few more fields inside the schema here. So let me first add key themes, and then I'll also add an import of annotated and an optional here. So these two imports will be essential for me. So key themes will actually be annotated list of strings. So what we can also do is we can also write a detail about this field here. So we can say that key themes must write down all the themes, all the important concepts discussed in the review in a list. And in the summary, I'm again going to use an annotated key, and inside this I'm going to write must write down must write down a brief summary of the review. Close this. Inside my sentiment, I'm again going to use an annotated. So with annotated, I'm going to say must return a sentiment value or sentiment of the review, either positive or negative, and I'll also add pros and cons here. So okay, I need to close this bracket at last. Also I need to do the same here. I'm also going to add pros and cons. So pros is going to be annotated, but this is going to be an optional list. If the model does not find anything like pros and cons inside the review, then it is not going to put it, or else if it finds something, then it will put it inside our pros list. So this is going to be optional str, and then write down all the pros inside a list. And also we'll do the same for cons. Annotated, optional, list of strings, and this will also be write down all the cons inside a list. Okay, so I'm going to add some more prompts to this, or some more details to this prompt here. So let me copy a prompt from somewhere. This prompt is from Google Pixel phone, and it is quite detailed here, so you can just pause the video and then type it if you want. I'm going to perform this word wrap for you so that it will be easier for you to type this. So this is going to be my prompt, and then based on this prompt, let me remove this, and then I will invoke a structured model here to see my result. So yeah, so let me go ahead and then run this code. So if I run this, as you can see with the structured output, the model's response is going to be kind of structured here. So the key theme is Google 10 Pixel Pro GPU performance, because it talks about the GPU performance somewhere around here with talking about its chipsets. Also it talks about the Tensor G5 chipsets, more gaming performance, comparison with Pixel 9 Pro, and things like that. The sentiment is mixed. It does not say positive or negative here, so we can also ask it to fix that, but like it is okay for now. The summary is also provided, and then the pros and cons, I don't think it's provided, because the model could not find, or the model could not identify the exact pros and cons in this particular review. Since this is optional, so the model could not write it. Or if we remove optional from here and then ask the model that it has to include the pros and cons, or like just the pros, the model will do that and then include all the pros of the review provided. So let's run this again. And then we see that summary is provided. Okay, what else is provided here? Summary is provided, key things is provided, sentiment is provided, and then it should also contain pros somewhere. Let me copy this and then see it in my copy. Let's open a JSON formatter window, if we can see the pros or not. So JSON formatter, paste my JSON here, and then we see that it still hasn't generated any pros here, but that's okay for now. Still our response is kind of structured here. So this is how we can take our structured response to somewhat another level, where we can include the details of what each of these keys that we want to include in the responses mean, and then what format should they be provided in. In our previous video, we explored structured outputs where the AI was guided to extract specific fields like summary or sentiment. That approach worked well, but the schema was relatively simple. Now we're taking structured output a step further by using Pydantic models to define a rich, detailed schema. So Pydantic is a Python library that allows us to create data models with type validation, default values, optional fields, and clear details. So this means that we can tell the AI exactly what kind of data we expect for each field, and we can trust that the output will conform to these types here. So by integrating Pydantic with LangChain structured outputs, we can define multiple fields like key themes, a brief summary, sentiment, pros, cons, and even the reviewer's name with strict validation. The AI then produces the responses that are not just structured, but also type safe, consistent, and fully compatible with Python applications. So this is especially useful when dealing with long or complex text. So instead of getting unstructured paragraphs, the AI learns to organize information into a machine readable object that can be directly used in dashboards, analytical tools, or database. And because of Pydantic's validation, we reduce the risk of errors like missing fields or wrong data types too. So the integration takes structured outputs from simple field extraction to a robust, reliable, and a developer-friendly approach. It also kind of ensures that the AI not only remembers the conversation context, but also returns precise, actionable, and validated information, making it ready for real-world applications. So let's go to the code now. So I'm going to create a new file here, and this is going to be 3 Pydantic structured output.py. Okay, so let's start. As always, we're going to use the same Gen AI model, import chat Google Generative AI. I'm going to install one more library here, which is called Pydantic. So include it in requirements.txt, and then I can directly install this using this command. And I also, okay, that is all for now because I don't have any emails right now, or else we would have to install some other libraries too. So what I'm going to do is from .env import load.env from typing import typedict. Import typedict. I'll also include an annotated literal and also a keyword called optional. Not sure I'm going to use each and every one of these though, but still we'll keep it in the import. So I'll import from Pydantic, import base model. And then I'm going to load my credential. I'm going to define my model. My model will be Gemini 2.5 Flash. Now I'm going to define a similar schema like we did in earlier code. So I'm going to define a class which will be called review, and the import will not be a typedict, but it will be a base model from our Pydantic class. So like I said earlier, I'm going to use a keyword called key themes, and instead of doing like annotated list of our content, what we'll do is we'll include a class called field here and then define this as a field. So this is going to be a list of string. Its type is going to be list of string, and its detail will be included in the field value. So I can include a field and then write down the details here. So write down 3 key themes discussed in the review in a list. The next is going to be my summary. My summary is going to be a string, and then I'll again write a field to write down the details of that summary keyword. Now this is going to be a brief summary of the review. I'll also write sentiment. And in case of sentiment, we had something like a mixed sentiment earlier, but I'm going to fix the model or ask the model to give either positive or negative sentiment here. So for that, I'm going to use literal. So one will be positive, one option will be positive. And then the other option is going to be a negative literal. So for that, I'm also going to write down the details. Description equals to return the sentiment of the review, either positive or negative. And this is going to guide my model to return either positive or negative here. Now I'll also include a name here. So name is going to be in string, and then I'll keep an optional keyword here because the names might not be available in the review, but if it is, then the model will definitely show the name too. So the description is going to be the name of the reviewer, or I'm going to say write down the name of the reviewer. Okay, so this is my output schema that I want my model to provide my output with. So I'm going to create a structured model. So this is going to be model dot with structured output, and then I'll provide my class, and then I'll also instruct the model to strictly follow the provided schema. Now let me provide my prompt. I can copy my prompt from the previous video or the previous code that I had. So I'm just going to copy everything else from now on here. So it is going to be a prompt, and then my prompt will be invoked using the structured model. And the code is complete. So let's run this code. Let me check if everything is all right. Okay, it seems okay. So let me run this. When we run this, the model output will be based strictly on the schema as provided earlier. Okay, so we have key themes. We have 3 key themes here, 1, 2, and 3 key themes. We also have a summary, and then okay, what else? We have a sentiment, which is strictly following the literals or the option that I provided here, and then the name is actually not specified. So if I change this prompt and then add a few texts, like add a name to this reviewed by Abhishek, then I'll see that the model also includes my name here. It should include my name here. Let's see the output. So yeah, you can see the name is being included, and then everything else is present based on the schema that we provided. In this video, we're exploring a powerful combination of LangChain features that help us control, structure, and process AI outputs in multi-step workflows. So there are 3 key concepts at play here. One is prompt template, second one is StrOutputParser, and the third one is chaining. So first, let's talk about prompt template. So prompt template allows us to create reusable, structured prompts with placeholders for dynamic content. Instead of hard coding every instruction for the AI, we can define a template once, specifying exactly what we want, and then fill in the variables as needed. For example, we can have one template that asks the AI to write a detailed report on any topic, and then another template that takes the generated block of text from the previous prompt and then generate a concise summary about it. So prompt templates gives us the consistency and control over how we interact with the AI which is crucial for predictable results. The next concept we have is StrOutputParser. So whenever the AI generates text, the raw output can be inconsistent. It can have extra lines, unexpected formatting, or maybe some minor variations in the wording. So StrOutputParser acts like this cleaning and standardizing tool, and it also ensures that no matter how the AI phrases its output, the output is converted into a neat, predictable string that we can feed into the next step directly. So this is especially important whenever we are building multi-step workflows, one after the other, because one wrong output can easily break the next prompt or the step in the process. Now, whenever we talk about multi-step workflows, we introduce this concept of chaining, where the output of one prompt becomes the input to the next. So by connecting these multiple prompts in a chain, what we can do is we can perform complex tasks that require several steps. For instance, let's say we first generate a detailed report on a topic using one template, parse it into a clean string using StrOutputParser, and then feed it into another template to create this short, concise memory. Now, this chain ensures that the flow of information is seamless, while templates and parsers gives us the control and reliability at each step. To summarize, the approach allows us to break down or decompose this complex AI task into structured and manageable steps. To summarize these three key concepts, prompt templates defines what we want and keep instructions consistent. StrOutputParser ensures clean and reliable outputs, and chaining lets us link multiple steps together to produce more advanced result. Now, when we combine these three together, we can build these multi-step AI workflows for real-world application. So now let's go into the practical implementation of these three concepts that we've just talked about. Okay, so I'm going to create a folder here, output parsers. Let's create a file inside this, StrOutputParsers.py. So let's import a model first, import Chat Google Generative AI. Let's also import .env, and then we'll import prompts from LangChain core. Prompt template. Okay, we'll do this first. We'll show how we break down the steps, and then we'll link up together using chaining at last. So first of all, I'm going to define a model. The model is the Gemini Flash model. Okay. Now, I will generate my first prompt using prompt templates. So first prompt, we'll define this using template 1. This is done using prompt template. The template detail is write a detailed report on topic. The topic is going to be a placeholder, but what will come inside that placeholder is this input variable, and this input variable is going to be my topic. Okay, if I need to invoke this, I can invoke this using this prompt 1 template 1.invoke. The topic is, let's say, English Premier League 2024 or 2023 2024. Okay, so this is my topic. If we want to check what kind of prompt it generates, we can run this and then see that using the prompt template, we can generate such kind of prompts here, right? Real report on English Premier League 2023-2024. Simply, this particular topic is going to be replaced here in the placeholder. Okay, I don't want to print this. Now I want to generate my second prompt. Second prompt, we'll define it using template 2. We'll use prompt template. And then the template details is going to be write a 4-point summary on the following. The placeholder is going to be text. Now after this, what I'm going to do is I'm going to define my input variables, which will be my text here. So based on this, I can again generate prompt 2. So prompt 2 is going to be invoked from template 2. Template 2.invoke, and then my text will be okay, where will my text come from? Okay, my text has to come from this first prompt here. So for that, I will have to invoke the model using this particular prompt here. So model.invoke. Okay, let's write this result 1, and then model.invoke. This has to be prompt 1, and then we need the content of this one, not the entire response, but only the content part or the text part. So here, what I'll have to put is I'll have to put result 1. Okay, now based on this, I'll have to again invoke the model prompt 2 prompt 2. Now I can print the result.content here. Okay, so here we've only used prompt template, the first concept that we've talked about. So we can define a template in such a way and then generate the prompt based on the template that we've created using prompt template, and then invoke the model. So but one thing that you need to remember here is result 1, if we only invoke the model and not print its content, this is not going to give me a standard string response here. So for that, what I need is I want to take out the content part of this result 1, but still I might not be sure that this provides me a string here. So for that, I'm going to do str result, just to be on the safer side, because the prompt needs to be a result here or a string here, because the content we pass in this particular text has to be a string. So now what we can do is we can print out result 1 to here, and then we'll run this model first, then we'll invoke StrOutputParser and chain later on. Let's also use a divider so that it becomes clear to us. Okay, now if I run this, I don't think I have any errors. Let me run this. Okay, let's go down up here. So here we have the result from the first prompt. So it is in fact giving me in terms of points. So this is a detailed report about English Premier League, and then from the second prompt we have a 4-point summary about the English Premier League. It is summarizing whatever text is being generated upwards here. Okay, this is working well, but we could have made this code a lot shorter here. So how do we do that? Now we introduce the concept of StrOutputParser to make sure that our output is in string, and then based on that we also introduce the concept of chaining so that we don't have to write 2 different invokes here. So now we're going to use that particular approach. So I don't need to clear anything much. I'm going to comment this out. I'm also going to comment these two lines out. I'll have my prompt 1. In fact, I don't even need to generate prompt 1, prompt 2. So I'll just have 2 different templates. I'll import StrOutputParser here. So LangChain core.outputParsers import StrOutputParser. Okay, I'm going to remove all of this so that you don't get confused here. So I don't need this. I don't need this. What I'll have to define is a chain. So my chain is going to be first invoke template 1, then invoke a model. Okay, I also need to define a parser here. So parser object from StrOutputParser class. Okay, so the model response needs to be converted into a standard string format using the StrOutputParser. Then after that, I'll have to invoke model template 2 first. Then again, I'll have to invoke the model, pass the prompt from template 2 to the model, and then use a parser again. So all of those steps can be reduced to this single step using the concept of chain. Now, to get the result, what I need to do is I just need to invoke the chain and not the model, because the model invocation process is already defined inside this chain here. So what parameter do we need to provide here? If we look at template 1, the entry point to template 1 is this particular topic here. So what we need to do is we just need to provide a topic inside this. The topic can be English Premier League 2023-2024. And then I can simply print out the result inside this, and still the model will work, but the model will only print out the output of this particular second template here. All of these in between tasks will be handled by this chain. So let's run this. It will take some time to run because there are 2 model invocations in between. So as you can see, we can directly see the output of this particular second template here, because everything in between is being handled by this chain, and the final result is a 4-point summary that we get from this particular topic here. So what is happening here? Everything that we did earlier has been happening here too, but since we're only printing the final result, we're seeing the final result here. So this concept of chain is very crucial in implementing such multi-step workflows that we talked about earlier. In our previous video, we learned how to use prompt templates to give the model clear instructions and how to use StrOutputParser to clean up the model's text responses. But what if we want the model to not just write text, but actually return structured data like proper JSON objects with specific fields? That's where the StructuredOutputParser comes in. Think of it like giving the model a blueprint for its answer. So instead of letting it respond however it wants, we define a clear structure. Like for example, we can say, give me 3 facts about black holes, and each fact should go into its own field. Fact 1, fact 2, and fact 3. So we define this structure using a response schema, which defines what each field represents. Then the StrocturedOutputParser uses that schema to make sure the AI's output follows the exact format we asked for. Usually that is a valid JSON object. Now, if you worked with LLMs before or you followed our video, you know that sometimes the model does not exactly follow the instruction perfectly. So it might miss a field, forget the brackets, or add some extra text. Now that's where the output fixing error or the output fixing parser saves the day. It automatically identifies when the output isn't in the correct format and uses the model itself to repair or reformat the response until it matches the required schema. So what we're trying to do here is we're really teaching the model to think structurally, to not just like generate sentences, but also to produce clean, structured content that a program can directly read and use. So this actually becomes powerful when we want to build systems like knowledge extractors, fact generators, or even data analysis tools where consistency matters. And just like we did in the previous video, we wrap everything inside a chain. So the flow looks like the following here. So the prompt first defines the task, the model generates the response, and the parser ensures the output is valid and well formatted. So the concept brings together everything we've learned so far: clear prompting, structured control, and automatic error correction, making our AI output also ready for automation. So now let's go to the implementation of whatever we talked in this video. Let me create a new file called StrocturedOutputParser.py. Okay, first model. We've been doing this since our first video, so I hope you understand this. Then the credentials. Then we're importing a prompt template from LangChain core. Then we'll import our output parsers here. So it will again come from LangChain core.outputParsers, import StrocturedOutputParser and a response schema. Okay, I did something wrong here. So this is going to be, oh, okay. So it does not come from LangChain core, but it comes from LangChain. So output parsers, import StrocturedOutputParser, and okay, something is wrong here. Oh, I should have written from, not import. So StrocturedOutputParser and then a response schema. Now from LangChain.outputParsers, I'll need OutputFixingParser to so this library allows the model to recorrect if there is any error in terms of its response. So load.env, I'll first define my model. Okay, now we'll define our schema here, or the response schema that we want. So basically we're going to pass our topic, and then we will ask the model to generate 3 facts, and then we'll create a placeholder using these response schema for those facts here. So for the first one, we'll call fact 1, and then its detail will be first fact about a certain topic. Okay, we'll say black hole. So this will be our first one. We'll again define a response schema. We'll have fact 2 and then add a description. So this will be second fact about black hole, and then we'll do a response schema again. Name equals to fact 3, description equals to third fact about black hole. Okay, so we'll define our parser. So this is going to be a structured output parser, but the structured output parser will be based on the schema that I have provided earlier. So structured output parser dot from response schemas, and then I'll pass in the schema here. So again, at last, if the model does not obey us in passing generating the output based on this schema, I'm going to use a OutputFixingParser from LLM. The LLM is going to be our model, and then the parser is going to be a parser which will strictly adhere the model to the given schema here. So now let me generate a template. So template equals to, I'm going to use this using prompt template. We've already done this earlier. So template will be give me 3 facts about topic. To write something more, return only valid JSON instruction that follows this format, and I'll provide a format here. Let me enclose this using string tag so that I can give multi-line strings here. So now the format will be format, or the instruction format, or we'll call it the response format here. So response format. The topic, the input variables at first is going to be our topic, and then I'll also define a partial variables for the response format that we provided here. So response underscore format, and this is going to come from parser dot get format instruction. So this particular parser will provide this schema or the response format to this template here. Now I'll create a chain where I'll pass in the template first, then a model first, and then the parser here. So first of all, the prompt will be generated using template, then it will be passed to the model, and then the model response will be fixed by the parser. Now I can invoke this chain using the entry point, which is our template. So I'll need to provide a topic here, and the topic will be black hole, and then I can print out the result. Let me clear this and run this again. Okay, I missed topic here, so clear this and run it again. There are a few spelling mistakes, but it's okay. I can see that I got a JSON format where I have fact 1, fact 2, and where's fact 3? Okay, I have fact 3, just like the way that we've asked for in our schema. So what is being done here? The prompt template is generating a prompt based on the template that we provided here. The structured output parser is asking the model to base its response on the basis of this provided schema here. The output fixing parser is strictly asking the model to follow this particular schema here. In the prompt template, one extra variable we provided is the partial variables. That partial variables is the response schema that we provided here, and then we've extracted it from the parser object of StrockedOutputParser, and then we've generated a chain and generated the response. So I hope this runs for you on your end as well. In our previous video, we talked about how large language models often gives us free-flowing text responses, and then how we can use tools like StrockedOutputParser to make those responses more organized and consistent. But now we're taking the same idea into a step further by introducing a much more powerful and professional tool called the Pydantic-OutputParser. So what exactly does it do? Now think of it in this way. So when we ask a large language model for structured information like someone's name, age, or city, the model tries its best to follow our instruction. But sometimes it gives extra text, sometimes it forgets a field, or sometimes it just formats things incorrectly. The Pydantic-OutputParser helps us control and validate those responses. So it makes sure the model's output isn't just structured, but also it's correct, complete, and reliable. This parser is built on top of a Python library called Pydantic, and Pydantic is all about data validation. It actually lets us define what kind of data we expect. For example, like we can say the name should be text, age should be number, and then it has to be greater than 18, and the city should be a word. So when the model gives us a response, the parser checks if everything fit those rules or not. If something is missing or invalid, the parser immediately flags it or even corrects it when combined with tools like OutputFixingParser. Now, if you remember the structured output parser we used earlier in the previous video, it also gave us structured data. So what is the difference between these two here? So the key difference is that the structured output parser mainly focuses on formatting. It helps the model respond in a defined structure. But the Pydantic output parser adds this layer of intelligence and validation on top of that. So it actually does not just organize the response, but it also checks the response and ensures that it matches the exact data type and the constraints we define. So that means we'll get fewer errors, cleaner data, and a far more predictable output, which is especially important when you're building real-world application. So the beauty of this parser is that once the model output passes through it, you can get a clean and reliable data ready to use in your code or application directly. Like you don't need to worry about converting things to string, fixing JSON, or like checking for missing fields. Everything comes out neat and validated exactly the way you want it. So the Pydantic output parser takes the concept of this structured output and then upgrades it with validation and reliability. If the structured output was our first step towards getting a structured response from LLM, then the Pydantic version is the professional grade tool, the one that makes your AI pipeline more stable and then production ready. So that is why this concept is so much important to understand, because as we start building more complex systems, we will rely on such kind of validated structured output to make sure our AI gives us the output in the format that we expect. So after this brief introduction, let's go to the code and see what we have talked about and implement it in real life. Okay, so I'm going to create a new file here. I'm going to call this Pydantic-parser.py. So I will have some import. First of all, our model. Then .env. Then I'll have my prompt template. Then I will have a Pydantic output parser. You can also use this output fixing parser if you want, but I'm not going to do this right now. I've already shown you how to use it in the previous video. So from Pydantic, I'm going to import base model, and then I'm going to import a field. Okay, so load the credentials, define the model, and after that, I'm going to create this Pydantic validation class called person. So here I'll have base model, and as a parameter, I'm going to include three things: name, age, and string. So name is going to be a string, its field and its detail is the person's full name. Then I'm going to have an age. Age is going to be an integer, and I'll also define its detail. So the age has to be greater than 18, and then it has to be less than let's say 100. Then I'll also add the detail or the description. The person's age must be greater than 18. Well, I've already defined that here. Now I'm going to define a city. It is going to be string, again field and its detail. So the city where the person lives. Okay, now I have defined this class. I'm going to create an object of PydanticParser, PydanticOutputParser, and then the Pydantic object is the class that we have defined. Okay, now let's create a template from the prompt template that we have. So the template is going to be, I'm going to create a multiple string or multi-line string here. So the prompt template is giving me, give me the name, age, and city of a fictional place person. Okay, what else? Make sure the age is greater than 18 and less than 100. Also return the response in following format, and the format is our response format, just like we did earlier. Okay, what else? I need an input variable. Input variable is going to be a place name, and then my partial variables is going to come from this is response format, and then it is going to come from parser or the parser object dot get format instructions. Okay, now what I can do is I can directly define a chain. So it will first call up template, then model, and then the parser. Then after that I can invoke this chain using the entry point to this chain, which is a place name. So let's say Nepal, and then print a result here. So the code seems to be okay. If you have any problem viewing this, let me do a word wrap so that you can see everything else here. Now let me run this code and see what we get in our response. We should get the name, age, and city just like we asked for. Okay, so if we see here, we see a name, Prakash Tahal, age is 45, and city is provided here, just like in the format that we asked for. So this is how we use PydanticOutputParser using LangGraph. So this is all for this video. I hope it runs in your end as well. In our previous video, we've already worked with simple chains, connecting multiple steps together, where the output of one step becomes the input for the next. Now we'll talk about a concept a bit deeper and talk about why chains are so useful and how we can make them more powerful using something called sequential chains. The biggest advantage of using chains is that they help us organize complex AI workflows into smaller logical steps. So instead of sending one massive prompt and hoping the model handles everything correctly, we break the process down. Maybe first generate something, then summarize it, and then finally maybe analyze it. This modular structure makes our workflow much more cleaner, more reusable, and then easier to debug. So if one part of the chain isn't doing well, we can just improve that step without touching the rest. So it's a very practical way to scale our AI projects. Now let's talk about sequential chains, which is one of the most useful type of chains in LangChain. So sequential chains work in a step-by-step manner. The output from one stage is automatically passed to the next stage in order. So think of it like an assembly line. So each component in the chain has a specific role, and together they create a complete workflow. So for example, step 1 could generate a detailed article, step 2 could summarize it into a few sentences, and then step 3 could maybe extract keywords or insights from that summary. The entire process runs very smoothly with data flowing automatically between steps. So now what's great about sequential chains is that they make complex reasoning tasks easier to redesign and control. So we can exactly fix what happens at each stage and then how information moves between them. And since everything is modular, we can mix and match our components, change a prompt, switch a model, or maybe add a new processing step, all without rewriting the entire pipeline. So in this video, we'll actually implement a sequential chain and see how it helps us combine multiple prompts and models into one connected process. And by the end of this video, you will be able to understand not how just to build one, or not just how to build one, but also why sequential chaining is one of the most powerful ideas in LangChain for creating intelligent and multi-step AI applications. So now let's go to the code. So I'm going to create a new folder here called, it's folder number 5 called chains. And inside this chain, I'm going to create my first chain called sequential chain.py. Okay, so again, first of all, we'll have a model. Then a .env. Then we're going to use our prompt template. So that is going to come from LangChain core. And then we'll also use this StrOutputParser that we've already used earlier too. And then that is also going to come from LangChain core. Load our credentials, define our model. Now I'm going to provide two templates. The first template will be a prompt template. We've done a similar example earlier too, but I'm going to use it anyway here. So generate 3 detailed report on a topic. I'm also going to use my input variables. My input variables will be a topic. So this is going to be my first prompt that will be generated from prompt template. The next will be another prompt that says generate a 3-point summary on following text, and then I'll provide a text here. So my input variables is going to be a text, and then I already have a model, so I'll define my parser, which will be from StrOutputParser, and then I'll define a chain, which is a sequential chain here. So first of all, I'll go to prompt 1, then I'll call the model, then I'll go to parser, and then I'll go to prompt 2, and then I'll again call a model, and then I'll go to parser again, and finally I'll invoke this chain and then store the output in the result. So chain.invoke, I'll define an entry point for this chain, which is topic. So my topic is going to be 3i interstellar. Okay, 3i atlas interstellar object, which is quite in news these days. So I'm going to use this topic, and then I'll just print out the result. So this here is a sequential chain here. So let me run this, and while this is being run, I'll try to explain you what's happening here. Okay, something's wrong. This is model name. So let me run this again. So we have our model. The first prompt is generated from this prompt template. The second prompt is generated from this prompt template. So based on the first prompt, we just pass to the model, and then the output is passed through the string output parser, which means the entire output will be converted to string, and then that particular output will be passed to this text here using prompt2 and the model, and then the output will be parsed again by StrOutputParser, and then finally be printed here. So it might take some time to run because we've called multiple models here. So let's see the output. Okay, we have a 3-point summary about 3i Atlas. So the first point is provided here, the second point is here, and the third point is here. The content is not that important right now. I just wanted to show you the implementation of chains. In our last video, we explored sequential chains where each step in the chain executes one after another in a fixed order. That was great for workflows that always follows the same path. But what if you want your AI workflow to make choices along the way? What if the next step depends on the output of the previous step? Now that's where the conditional chain comes in. So conditional chains lets you design workflows that branch based on certain conditions. So instead of a single fixed path, you can define multiple possible paths, and the chain decides which one to follow depending on the model's response or some other criteria. So think of it like you choose your own adventure book. Depending on your choice, the story takes a different direction. Conditional chains give your AI workflows that same flexibility. Okay, let's take an example. So imagine you're processing customer feedback. So if the feedback mentions a bug, you might want to send it to the development team. If it's a feature request, you might want to send it to a product team. And if it's a compliment, maybe you log it and then thank the user automatically. So with a conditional chain, the workflow evaluates the content and routes it automatically. You don't have to manually check each case. The chain handles the branching logic. So the real advantage of a conditional chain is that they make your workflow dynamic and intelligent. So you're no longer limited to linear processes. Instead, your AI can adapt its upcoming step based on the data it sees. Now, this is incredibly useful for real-world application where inputs can vary widely, like customer support, content analysis, data classification, and much more. So in this video, we'll implement a conditional chain and see exactly how to set up multiple paths and conditions. So by the end of this video, you'll understand how to create a flexible AI pipeline that responds intelligently to different situations, making your applications more robust and closer to human-like decision making. Now, let's jump onto the code. Okay, I'll create a new file here and I'll call it conditional chain.py. First of all, we'll have our model, then a .env, then I'll have my prompt template, then I will have the Pydantic-output-parser, which will come from LangChain core .output parsers import Pydantic-output-parser. Then I will use this Runnable schema.runnable import Runnable branch for branching chain logic, and then Runnable lambda for a lambda function. Since we're using Pydantic models, so we'll include a base model and a field. And also, let me write this literal class from the typing function. Load the library, load the model, Okay, now I'll also have one more parser, which is the StrOutputParser. So my parser object will also be created, StrOutputParser. Now I'll create a Pydantic class here for feedback. So this will be a base model. I will try to find the sentiment of the feedback, which will have two options. It can be the positive feedback or a negative feedback, and then its detail will be given here, field, and description is the sentiment of the feedback provided. Okay, I will have a parser 2, which will be my Pydantic parser or Pydantic output parser, and then the Pydantic object will be my feedback class. Now I'll have a prompt 1, which will be my prompt template. Prompt template. Its template will be classify the sentiment of following feedback text into positive or negative, and then this will be my feedback placeholder. So input variables will be feedback, and I'll also have a partial variable because I'll provide a format instruction here, classify sentiment and provide the response in following format, and then this will have our response format. So I'll have a partial variable. Okay, this has to be a dictionary. So response format is going to come from parser2 dot get format instructions. Okay, I'm going to use a word wrap so that it will be easier for you to view here. Word wrap. Okay, this is my first prompt here. I'll first define a classifier chain, which will follow prompt 1, model 1, or the same model that I have. I'll just use the model, and then parser, and then parser 2, because I'm going to use the Pydantic parser here. Next, I'll again have another prompt, which is going to say template write an appropriate feedback to this appropriate response to this positive feedback, and then I'll provide my feedback here. I'll have an input variable. This will be feedback, and I also have prompt 3 that will work for the negative feedback. So negative feedback, and then the value will be prompt 3. So here I'm going to declare a branch chain. As we can see, this is a sequential chain we have here, but based on the output of this chain, now we'll move on to the branch chain and then either select one of these two prompts and then generate the response. Now for branching, I'm going to use Runnable branch, not this bracket. I need a small bracket here. So Runnable branch, I'm going to declare a lambda function here. So lambda x sentiment equals to positive. So if the sentiment is positive, then my chain will be prompt2 model and then parser. Else, if my sentiment is negative, lambda x dot sentiment equals to negative, then my chain will be prompt3 model and then a parser. And I need to declare this as a runnable lambda. Lambda x. So if, else if, and then the last one is else condition here. So if the sentiments are either of these positives and negative sentiment, then I'm going to say no valid sentiment found in my review or feedback. Okay, the bracket should not close here. So this is done. Now what I'm going to do is I'm going to combine these two chains into one chain. So first one is our classified chain, and then the second one is our branch chain. So we can also combine a sequential chain and a conditional chain into one single chain here like this. The first one that is going to be executed is our sequential chain or the classified chain, and then based on the response of the classified chain, we will then move to branch chain, and then the model will work accordingly. So we'll invoke this chain dot invoke. The entry point is the classifier chain, and then in the classifier chain the entry point is feedback 1, or sorry, prompt 1, where I need to provide a feedback here. So let me provide a feedback and then say that the phone is actually amazing. Let me print the result and see what we get here. It should actually trigger prompt 2, and then we should get an appropriate response for this positive feedback here. So let's run this. So now we see that we get a positive response, and then there are the model classifies this feedback as positive, and then based on it, it generates a response. Now I'm going to change this. Okay, the phone is actually horrible, the UI is stuck, and then things like that. UI is stuck, and then if I run this, so the model is in fact giving out a lot of things, but you know that we can structure the output using the Pydantic-OutputParser or this or like we can base it on some form of schema, as we've already done earlier. So you can actually implement it yourself. So here we get that the response. Okay, so it says that when responding to negative feedback, so it classifies the feedback as negative here for this thing. So in this video, we saw how we could implement conditional chains using runnable branch, runnable lambda, as well as how we could combine a sequential chain and a conditional chain into one, and then make our workflow automated here. So far in the series, we've explored sequential chains where each step executes one after the other, and conditional chains where the workflow can branch based on certain conditions. Now we're moving into another powerful concept in LangChain called parallel chains. So what exactly is parallel chain? So in simple terms, we can say that parallel chain allows us to run multiple workflows at the same time, independently of each other, and then combine their results. So think of it like a team working on various tasks simultaneously. So one team member is taking notes, another is taking or like creating quiz questions, and then later on someone merges both into a final report. So by doing things in parallel, we can save time, make the workflow more efficient, and then handle multiple aspects of a task at once. And then that is also key advantage of parallel chain, efficiency and modularity. because each component can focus on a specific task without waiting for the others to finish. And once all the parallel tasks are complete, the output can be combined in a meaningful way, creating a complete and comprehensive result. So what are we going to do in this video? So our plan for this video is, first, we'll take a block of text. Then we'll run two parallel tasks. One will generate short and simple notes from the text, and then the other will generate a set of short quiz questions based on the same text. And then finally, once these two parallel tasks are done, we'll merge the notes and the quiz into a single comprehensive document. This will show exactly how parallel chains can handle multiple output at once and then combine them seamlessly, making our AI workflow both fast and organized. Now, let's jump onto the code. So create a new file called sequential parallel chain, not sequential chain, parallel chain.py. Okay, first of all, our language model, then a .env function, then I need a prompt template which will get from LangChain.prompts. Let's also use the StrOutputParser. And we'll have a RunnableParallel from LangChain.schema.runnable for our for our parallel chain to run here. Okay, now let's load the credentials, define our model. Now, first of all, I'll define a prompt. First prompt will be about generating a short and, like, let's say, generate short and simple notes for or from the following for the following topic. For the following topic, we would place a topic in the placeholder. Our input variables is going to be topic. We're not going to enforce any kind of schema for our response right now, so we'll just leave it to this. Our next template will be a prompt template, and this will be about generate 5 short question answer from the following text. Our input variable is going to be a text, and then after this I'll have prompt 3, prompt template. This will generate okay, short question answer is done, and then the summary is also done, right? So we will have prompt 3 to merge the provided notes and quiz into a single document. Then I'll provide notes in notes placeholder, and then quiz in quiz placeholder. Okay, so now let's create an object of our parser here. So parser equals to StrOutputParser. I'm going to create a runnable chain or a parallel chain, which will be done using RunnableParallel. The first component of this chain is to create nodes, and I'll name it nodes. How we'll run this is We'll first start with prompt 1, then pass it to the model, and then model, and then run a parser on it. In the second chain, we'll name it quiz. We'll pass prompt 2, then model, and then a parser. Okay. Now we'll call our final chain, which will be prompt 3, and then model, and then parser. Now we'll combine the sequential chain here, final chain, and then the parallel chain, runnable chain here. We'll call it chains equals to, first of all, we'll execute our runnable chain, and then we'll execute our final chain. We'll invoke this chain dot invoke, and then we'll provide an entry point for this one. So the entry point to this chain has to be a text, right? So a topic or a text here. Okay, I'll just try to make it uniform, but it's okay even if we don't make it uniform, because one is going to go in topic and then the other is going to go to text. I think I don't need to make it uniform, I guess. So let's write a text here. I'm going to copy this text from someplace else, but I will be using a word wrap so that you can copy this, or like use any text that you want from anywhere. So this text is about support vector machines. View word wrap. Okay, everything is wrapped inside this view. Now what I'm going to do is I'm going to invoke this. Simply invoke this text. The result is going to be stored here. Result equals to chains.invoke, and then finally I'm going to print my result. So this is my parallel chain implementation here. Let me run this code and then I'll explain what is happening here. Okay, while the code is running, let's go up. We have prompt 1, which generates a short and simple note about a following topic. Prompt 2 is like generating short answer question, the following topic. And then prompt 3 is about merging the output from prompt 1 and prompt 2. We have a parser, and then I have initialized a runnable chain where we run these two chains in parallel at first, and then the output of these two chains are then merged with the final chain, and then a response is created. So if we see here, so basically a complete node is created where we have support vector machine nodes. The node is created here on top, and then the quiz is created here on the second, and then both of these are combined into one comprehensible documents. So this is how we implement parallel chain in LangChain. So I hope this runs on your end too. If you have any questions or if you have any queries, feel free to comment down below and I'll try to help you out. I will see you in the next video again. So now we see that we get a positive response, and then there are the model classifies this feedback as positive, and then based on it, it generates a response. Now I'm going to change this. Okay, the phone is actually horrible, the UI is stuck, and then things like that. The UI is stuck, and then if I run this, so the model is in fact giving out a lot of things, but you know that we can structure the output using the Pydantic-OutputParser or this or like we can base it on some form of schema as we've already done earlier. So you can actually implement it yourself. So here we get that the response. Okay, so it says that when responding to negative feedback, so it classifies the feedback as negative here for this thing. So in this video, we saw how we could implement conditional chains using Runnable branch, Runnable lambda, as well as how we could combine a sequential chain and a conditional chain into one, and then make our workflow automated here. We've explored different types of chain, sequential chain, conditional chains, and even parallel chains. Each of these help us design multi-step workflows and process information in a structured way. Now let's focus on something simpler, the LLM chain. So what exactly is an LLM chain? At its core, an LLM chain is just a single step chain. It connects a language model to a prompt template, letting us easily generate outputs from our LLM in a structured and reusable way. Think of it as a building block, a straightforward chain where we give a prompt, the model processes it, and then gives an output. There's no branching, no parallel processing. It is just a simple, clean workflow for a single task. The beauty of LLM chain is in fact in simplicity and reusability. So for example, you might want the model to suggest a catchy blog title, summarize an article, and generate ideas for social media tasks. So you create a prompt template for the task, connect it to the model via the LLM chain, and then you can get, or you can reuse that chain for any input without rewriting your logic. So in this video, here's what we'll do. We'll define a prompt template asking the model to suggest a catchy blog title for a given topic. We'll connect it to a language model using LLM chain. Then we'll run the chain with a specific topic. And finally, we'll see how the chain returns a creative, usable blog title. So the following implementation is going to demonstrate how LLM chain provides a structured, repeatable, and simple workflow for generating AI outputs. So without any delay, let's go into the code. So I'm going to create a new file here. I'm going to name it LLMchains.py. As always, we'll first use our model, import chat Google generative AI from .env, import load.env from LangChain_core.prompts. I'm going to import a prompt template. And the new concept today is from LangChain.chains, import LLMchain. Okay, so first of all, load the credentials. We'll load a model, Gemini 2.5 Flash. Then we'll create a prompt, which will be used using prompt template. I'm going to write a template for this one. So suggest a catchy blog title about a topic, and my input variable is going to be a topic. Okay. Now I will define a chain which is going to be an LLM chain, and I'm going to pass a model to this and then a prompt to this. Okay, and then based on this, let me write a topic name. Let's say 3I Atlas interstellar object. I'm going to invoke this chain. So response equals to chain dot invoke. I need to provide a topic here. So topic is going to be my topic variable. And then basically I'm going to print the response to this. So everything is done. Let me clear this. I'm not sure about this LLM chain. It might be deprecated or something. Let's see. Okay, so this is deprecated with the method, okay, RunnableSequence. So we've already done RunnableSequence earlier, but it's okay. We're doing something that has already been deprecated, but still we get our answer here. The topic is 3I Atlas interstellar object. Here are some catchy block titles. Since we have not structured or directed our response to be something specific, that's why the model is generating this long text here as a catchy block title, which we don't in fact want, but like it is what the model is providing me. So here's what you can do. You can use some form of response schema or maybe a Pydantic class to direct the model to provide just a catchy block title, just a combination of 3 to 4 words block title for this particular topic. So I'm going to end this video for now. If you have any problem or any queries, do comment down below and I'll try to help you out, and I'll see you in the next video. In our previous videos, we've worked with LLMs and chains, giving prompts and generating responses, and even combining multiple models to create structured workflows. Now we're moving into another fundamental concept that powers intelligent retrieval, search, and reasoning in modern AI agents: embeddings. So what exactly are embeddings? Think of embedding as the numerical fingerprints of text. So when we feed a sentence like Delhi is the capital of India into an embedding model, it doesn't just read it as words. It converts that text into a vector, which is a list of numbers. Each number in this vector represents a small piece of meaning from the original text. Together, they form a semantic representation, meaning that two texts with similar meaning will have vectors that are close to each other in this higher dimensional space. So we'll make this intuitive. Suppose if you take two sentences like Paris is the capital of France and Delhi is the capital of India, the embeddings will be very close because both talk about capital cities. But a sentence like I love pizza will have a completely different embedding far away in vector space. Now, why do we need embeddings? Embeddings are basically essential whenever we want our AI to understand the context or meaning rather than just a plain text. They help us with semantic search, meaning finding documents similar in meaning, not just by matching keywords. It also helps in context retrieval. That means fetching relevant chunk of information to feed into an LLM. They help us with clustering and classification, which means grouping related ideas together, and they help us with recommendation system, meaning suggesting similar product or content based on its meaning. So in this video, we'll use Hugging Face embeddings, specifically the model. In this video, we'll use Hugging Face embeddings, which is a lightweight and efficient. In this video, we'll use Hugging Face embeddings and a lightweight model from the Hugging Face embeddings. So we'll generate embeddings for a single query, that is the Delhi is the capital of India, and then a list of related documents. Then when we print them, we'll see a long list of numbers, and those numbers will be the numerical representation of our text. But what's more important is that we will use those embeddings to compare similarities, store them in a vector database, or build context-aware AI agents that retrieve information intelligently. So the main advantages of these embeddings are huge. First of all, they allow semantic understanding, meaning the model can reason about meaning rather than exact wording. Second, they make retrieval augmented generation possible, or RAG possible, where an AI can look up context before answering. And the third, they significantly improve accuracy in search, question answering, and knowledge-based systems. So embedding acts as a bridge between the language and numbers, allowing machines to understand and compare the meaning of provided text or document. And as we go further in this series, we'll see how embedding power intelligent agents, enabling them to remember, reason, and respond more accurately. But for now, we'll see the very basic implementation of these embeddings. So let's go into the code. Okay, I'm going to create a new folder here and then call it embeddings. After that, I'm going to create a new file. Let's call it Hugging Face Embeddings .py. Hugging Face Embeddings .py. Okay, now the import is going to be quite different here. So first of all, I think I'll need to install something. Let's go to requirements. Here I'll need to install LangChain _ Hugging Face. Okay, I'm going to install these requirements. As everything else is installed, the new library will also be installed in addition to the other libraries that we already have. Okay, this is installed. Let's go back to our code, and then from here we'll import from LangChain _ Hugging Face, import Hugging Face embeddings, and we'll import .env, load.env, and then we'll also import OS. I'm not sure if this is going to be used or not, but anyway, let's import it, and I'll load my credential. Okay, so what kind of credential am I loading here? So to use Hugging Face embeddings, you need to visit the Hugging Face website and create your API key and then save it in the environment file here. So you can do that yourself or take the reference from the Hugging Face documentation too, or the LangChain's documentation, and then you can create that Hugging Face API key and then paste it in your env, and then that will be loaded here using this load.env function. Anyway, I'm not going to go to that. I've already placed my Hugging Face embedding key here, so I'm directly going to run this. So embeddings equals to Hugging Face embeddings, and then I'm going to use a model here that I found out in the Hugging Face model section. So this model is sentence transformers all mini LM L6 V2. I might also need to import sentence transformers here. So let me write that down and then install the requirements. Pip install -r requirements.txt. So while that is being installed, let's continue with our code. As I said, I'll have a text, simple text. Delhi is the capital of India. And along with this, I'll have some documents where I'll say Delhi is the capital of India. Kolkata is the capital of West Bengal, and then Paris is the capital of France. So what we can do here is, like I said, we can convert this textual data into numerical figures. So to do that, I'm going to use embedding model dot embed query, and then inside this I'm going to pass this text here. So if you print this out, str result, if you print this out, then you'll see that this particular text will be converted to numbers. Okay, so let me run this now. The library is now installed. I can run this code now. It will take some time to run because the model might not be downloaded. So it will download the model first and then run our program here. Okay, so once I printed this and the code has run, we can see that this particular text is now converted into this combination of numbers here. Now this is called embeddings. Not only this, we can also embed our documents here. So if I just type result underscore doc equals to embedding dot, since we are embedding documents, so we need to pass in embed documents and then pass in the documents in this list. Now if we print this, we'll see that we have embeddings for each of these text in a document. So we'll basically get a list of embeddings, and then each embedding will resemble each sentence that we see here. So I think you can run this program on your end and then see the result of your embedding here. What we'll also do is we'll also try to compare the similarity of this particular text with these documents here. So let's see what happens. What we'll do is we'll do result here and then result doc here. Now we'll compare the similarity score, and then for the similarity score we'll use cosine similarity. For that we'll need to import something here, or basically need to install a library. Let's install pip install scikit-learn, and then based on that particular scikit-learn library, we'll import from sklearn.metrics.pairwise. We'll import cosine similarity. And now to compare our similarity embeddings between our text and our document, we'll use cosine similarity and we'll pass our result here, the result, which is the embedding of our text, and then we'll pass our document embeddings, which is result underscore doc. So let me print out the similarity scores here. So let me simply print out similarity scores, whatever we get here, and then run this program again. So as you can see, the text is the similarity between the text and then the first document is almost 98%. Similarity between the text and the second document is almost 47%, and the third document is 27%. Now if I add a new sentence like I love pizza here, we'll see that this similarity score is quite low in comparison to the above three sentences. Let's print it out. Let's clear this and then run this model again. So we can see that the text Delhi is capital of India is very much lower similar to I love pizza, which is almost 9% similar to pizza. So the highest similarity is these two sentences. You might get why we did not get 100% similarity, because here there is a slight mistake while I've typed this word. So if I type Delhi is the capital of India and then we get the same sentence here, it would basically be 100%. Let's see if we get 100% similarity between them or not. So yeah, we get 100% similarity score between these two sentences. So this is the importance of embeddings, basically converting the text into numbers represent the semantic meaning of that particular text, which is easier for computer to understand. And everything from now on that we'll do will be based on these embeddings. Basically, if embeddings were not possible, retrieval augmented generation would not have been possible. In the last video, we explored the concept of embeddings, how they transform text into numerical representation that capture meaning. Now we're taking one step further and actually use those embeddings to make our model retrieve and reason over real data. So in this video, we'll build a simple retrieval augmented generation or a RAG pipeline, a system where the model doesn't just rely on its internal memory, but instead looks up relevant information from external sources before giving an answer. So we'll break down step by step. The first thing we do here is load a document using a text loader class. So it's a straightforward way to bring in external data, for example, a text file, a web page, or even a PDF. Here, we're going to use a TXT file, which might contain note, research summaries, or articles. Next, we use the recursive character text splitter. Now, this is a very clever tool. What it does is it breaks large text into smaller manageable chunks, usually around 500 characters each in our case. But why do we do that? We do that because language models and embeddings work much better when the text is short and focused. So by giving them the bite-sized chunk with slight overlap, we have the model preserve the context while avoiding cut-off issues, especially useful when dealing with large documental books. Now, once the text is split, we move to the embedding step. So here we're going to use Google's Gemini embedding model. Each of these chunks will be now converted into a vector or embedding, just like we saw in our last video. Now these embeddings need to be stored somewhere efficiently, and that's where FAISS comes in. So FAISS stands for Facebook AI Similarity Search, and it is a powerful open source vector database that allows us to store and search documents very quickly. So using FAISS, what we do is each chunk of our content is embedded into a vector, and then those vectors are stored in a FAISS index, and FAISS prepares itself to find the most similar vectors whenever we search. Then we'll go for something called a retriever. So what happens in a retriever is it is like a search engine for our AI agent. So when we provide a query, for example, like what are the key takeaways for our documents, the retriever searches through all those embeddings inside FAISS and then returns the most semantically similar search. So this step ensures that our model doesn't try to remember everything. Instead, what it does is it retrieves the right information on demand. So after that, we combine all of those retrieved text chunks into a single string of context. This context acts like the background material or notes that we pass to our language model. Then finally, we initialize our Gemini chat model and manually construct a prompt that combines both the context and the question. So when we pass this prompt to the LLM, it uses the provided context to generate a factual, context-aware answer, and then not something made up from its internal knowledge. So this workflow is the backbone of what's known as retrieval augmented generation or RAG. Instead of letting the model guess or hallucinate, we ground it with real retrieved data here. So the benefits are huge. The model gets more accurate and reliable. It can also handle custom data sources, and it's far more scalable since we can swap documents, add new data, and then do something like that. So in this video, we will take a big step from embeddings to retrieval. Now let's go to the code. So I'm going to create a new folder here and call it RAG or basic RAG for now. Let a new file, basic rag.py. What I'm going to do is I'm going to create a docs.txt file and then bring some paragraphs of content here. I already have it. So I'll have this content about AI. I'm going to do word wrap. You can bring anything else that you want here. It's fine. So yeah, this is my document for now. Okay, we'll go back to our basic RAG model. So I'm going to generate my model first. Then .env I'm also going to load a text loader from LangChain community. Then I'll have a text splitter from LangChain. Then let's also import our embeddings from Google Gemini. Then we'll use VectorStores to store our embeddings here. And then we'll use a retrieval QA. So from LangChain chains put retrieval, not this one, retrieval QA. Okay. Now based on this, first let me load the credentials. Load the credentials. Okay, I'm providing stepwise information here. So step 1, I'm going to load my credentials. In step 2, I'm going to load the document that I have. So I'll be defining a loader and then using this class here called text loader. My file name is docs.txt, and then I'm going to load this. So documents equals to loader.load. In step 3, I'm going to split the text into smaller chunks. So for this, I'm going to use a text splitter, recursive character text splitter. I'm going to define the chunk size of each splitted text. Let me give 500, and then also chunk overlap, because we might carry some contextual information in while breaking those chunks, so we want some overlap so that two different chunks can have something in common between them. So I'm going to split my document using this splitter. So text splitter dot split documents. Okay, now I'm going to, okay, this is step 3. I'm going to step 4, where I'm going to convert text embeddings and store in files. So here what I'm going to do is I'm going to define embeddings equals to Google Generative AI Embeddings, where the model is model / Gemini embedding 001. I found this in the LangChain documentation itself. And then I'm going to define a vector store using phase dot from documents from documents docs comma embeddings. Then in step 5, I'm going to create a retriever which fetches relevant documents. Okay. A retriever equals to VectorStore dot as a retriever, and then I'm going to initialize a model. So model equal to chat Google Generative AI, model equals to Gemini 2.5 flash. You can even use Hugging Face models here. Step 7, I'm going to create a retrieval QA chain. So chain equals to retrieval QA dot from underscore chain underscore type. where LLM equals to LLM and a retriever equals to a retriever, LLM or model here. Then I'm going to manually query the model and retrieve relevant documents. So query is going to be like, okay, what is the document about? Let's see. So it is about AI. So my query will be very simple. So what are the key takeaways from the document? And then based on this query, I can invoke my chain here. So chain dot invoke query, and then finally I'm going to print my answer. So print response. Okay, the code is done. I have tried to provide you stepwise implementation of what we talked about in the RAG pipeline. So let me run this. Let me also save this document and then run this here. So the model will provide answer based on, okay, I need to install something here. So 5 CPU needs to be installed. Let's write it down in requirements.txt2. 5 GPU, install this with install -r requirements.txt. Okay, we can install the CPU version because my laptop not be equipped with GPU here. Okay, so let me run this once again. And while this is being run, the answer from the LLM is based on the documents that I provided and not on its internal knowledge base. So the key takeaways are like actually provided here. If we need to ask something specific from this document, like what is this? So doing such tasks such as learning, reasoning, AI comprises very okay. What kind of technology that AI comprise? Let's ask that. So what kind of technologies does AI comprise of? So if you ask this question, then the model is going to provide the answer based on the document and not its internal knowledge. So it says AI comprises a variety of technology. It's copied just from this particular context here. So this is how we build a basic RAG pipeline. I hope you understood the concept. We've been exploring how different types of chains help us connect multiple components together, from simple prompt to model pipelines to more advanced parallel and conditional chains. But now we're going one step further and introducing a concept that gives us even more control and flexibility in how our data flows through a chain. Runnable sequence. So what exactly is a runnable sequence? So think of it like a conveyor belt for data. Each step in the sequence takes the output from the previous step, processes it, and passes it along to the next one. It's part of the new Runnable interface in LangChain, which unifies how different components like prompts, models, and parsers communicate with each other. Earlier, when we worked with LLMChain, the structure was quite fixed. One prompt, one model, one output. It worked great for single or simple workflows. But when we wanted to do something more dynamic, like taking a model's output, processing it through another template, and then feeding it back to another model, things start to get messy. That's where a runnable sequence shines. It lets us build multi-step pipelines where each element can be a model, a parser, or even another chain, all connected in a single streamlined sequence. You can think of it as a customizable chain where you fix exactly how data flows from one step to another. Now in this video, we'll be doing something fun to demonstrate it. We'll start with a prompt that asks the model to write a joke about a given topic. Then we'll take that generated joke and then feed it to a second prompt, one that asks the model to explain the joke. And then finally, we'll use an output parser to cleanly process and present our final response. So by the end of this video, you'll understand how runnable sequence works, how it is different from earlier chain structures we've seen, and how you can use it to build smooth multi-step reasoning pipelines where the model's output becomes the input for the next steps. All right, so let's dive into the code. So I'm going to create a folder here called Runnables. And then a file called RunnableSequence.py. Okay, so first of all, import LangChain Google Gen AI. Then I need a .env. After that, I'm going to import prompt template, which will come from LangChain core. Then I will import an StrOutputParser that is also going to come from LangChain core. From LangChain core. From LangChain core.outputParsers import StrOutputParser, and after that I'll need a runnable sequence which will come from langchain.schema.runnables import RunnableSequence. Okay, so first of all, load the credentials. I'll define my first prompt where using my prompt template, and then the template is going to be about write a joke about a topic, and inside this my input variables is going to be topic. I'll similarly write second prompt again using a prompt template where my template will be explain the following joke, and then I'll type in joke here. My input variables is going to be joke. Okay, so my model will be from Chat Google Generative AI. The model will be Gemini 2.5 Flash. I'll also define my output parser using StrOutputParser, and then based on that I'm going to define a chain or a runnable sequence. So first of all, I'm going to go to prompt, then I'll go to model, then parser, then prompt2, then model, and then parser again. And then the result, I'll just invoke this runnable sequence. Invoke. So the topic is going to be a monkey. And then finally print a result here. So this is how you implement runnable sequence. You might see that this is similar to the concept of chains that we've used. If we had used chains, we would do it in this way. So change would be prompt model parser, then prompt 2, then model, and then parser again. So this is how we would implement chain. But here we're doing it with RunnableSequence. Let me run this code. It will take some time because we have multiple model calls here. One model call is this part, and then the other model call is this part, and then without the completion of the first model call, we cannot go to the second model prompt here. Okay, so couldn't feel the love anymore, so the humor breaks down. Okay, it's only printing me out the explanation about the joke, but it's okay. It's okay because I've got what I wanted at the end of this runnable sequence. In the last video, we explored RunnableSequence, where each step in the chain passed its output to the next, creating a smooth step-by-step flow of data. But now we're flipping that idea around and diving into something that works side by side instead of one after another, which is RunnableParallel. Simply put, RunnableParallel allows us to run multiple sequences or tasks at the same time in parallel. While RunnableSequence is all about order and dependency, where step 2 awaits for step 1, RunnableParallel is about independence and speed. Each branch runs simultaneously on the same input, producing multiple outputs at once. So imagine you're a content creator and you have one topic, say AI, and you want a tweet, a LinkedIn post, or maybe an Instagram caption about it. So instead of generating them one by one, RunnableParallel lets you generate all of them in a single call. So that's exactly what we'll be doing in this video. We'll create two separate prompts, one to generate a tweet and another to generate a LinkedIn post about the same topic. Then we'll wrap them inside a RunnableParallel. So both prompts are executed at the same time using the same model. The final output will give us both results neatly, one as a tweet and then the other as a LinkedIn post. So the real advantage here of RunnableParallel is efficiency. When you're building complex AI workflows like summarizing document, generating multiple content format, or running multi-perspective analysis, RunnableParallel helps you process everything faster and more efficiently without waiting for one task to finish before starting the next. So in this video, we'll see RunnableParallel in action, understand how it complements RunnableSequence, and also explore how combining both can help us build truly powerful multi-step, multi-output pipelines. So let's get started and then go to the code. So I'm going to create a new file called RunnableParallel.py. I'll be using the same import, so I'm just going to copy it from here, okay? So these three imports are the same. These four imports are the same. And then I will need to call up RunnableParallel and RunnableSequence here. So LangChain dot schema dot runnable import runnable sequence and then runnable parallel. Okay, so this is also same. I'll have prompt 1, which tells me or which is about generating a tweet. So generate a tweet about topic, and then the input variables here is a topic, and another prompt is also the same, so I'm just going to copy this. So prompt 2 is generate a LinkedIn post about a topic. So this is going to be prompt 2. I'll define my model. So model equals to Chatbots generative AI, model equal to Gemini 2.5 flash. We'll also have a parser. So parser equals to StrOutputParser. And after that, I'm going to implement a parallel chain using RunnableParallel. So parallel chain equals to RunnableParallel, and inside this, I'll have two different runnable sequences. Okay, so the first one will be named tweet, and inside this, I'll have a runnable sequence. Tweet. It is going to be a runnable sequence where I'm going to pass in prompt, one model, and then parser. And similarly, I'll also have second runnable sequence. It will be about prompt, two, model, and parser. Now, going to invoke this parallel chain dot invoke. The topic is going to be we will do runnable parallel in LangChain, and then I'm going to print the result. So this is how we implement a runnable parallel in LangChain. We'll need runnable sequences for individual parallel events here. So let me run this and then see the output. Again, it is going to take some time to run because I have multiple runnable sequences here. So these two need to be implemented, but they'll be implemented simultaneously at once. And then I'll get the final output here. Also, if we need to maybe bind our output in some form of schema, we know that we've already done that. We can do it using Pydantic, or maybe by defining some form of schema, and then we've done it in our earlier videos. If you haven't seen that, you can go back and then check it out and try it yourself. So here we have a tweet. And then down here, we also somewhere have a LinkedIn post that we need to find, but at least it's there somewhere. It is there somewhere around there. And then in case of LinkedIn post, I think I'm getting some code to here, like these lines, I think are the codes here. So anyway, we have implemented a runnable parallel in this particular program. Today, we're diving into one of the most essential building block of any LangChain project, which is document loaders. So if you've ever wondered how we bring data from the real world like PDFs, text files, websites, or CSVs into our AI pipeline, this is where it all begins. So document loaders actually act as a bridge between raw data and intelligent system. So what exactly are document loaders here? So think of them as a specialized tool that read and import data from different sources into LangChain's standardized format called documents. So each document contains not just text, but also metadata, things like file name, source URL, or page number, which later helps us organize and query data more efficiently. In simple terms, they are the data ingestion engines of LangChain. And today we'll look at five of the most commonly used ones: text loader, PyPDF loader, directory loader, web-based loader, and then CSV loader. So first of all, we'll start with the text loader. As the name suggests, this one deals with plain text files. So it's perfect when you have .txt documents, maybe transcript, logs, or notes that you want to feed into your system, where it opens the file, reads the text, and wraps it into a LangChain document object, which is quite lightweight, fast, and ideal for structured plain text data. The next is a PyPDF loader, one of the most popular loaders, especially in retrieval-based AI system, because PDFs are everywhere in research paper, invoices, reports, books, and they often carry a lot of valuable information. So PyPDF loader extracts the text from each page and converts them into a structured documents, keeping track of the metadata like page numbers and file sources. And then it makes it incredibly useful when you need to query or summarize specific sections of a PDF rather than treating it as a single long text. Now, what if you have hundreds of files sitting inside a folder? And that's where document loader comes in. Instead of manually loading each file, directory loader. So directory loader scans through your folder and automatically loads every document that matches your design pattern. For example, all TXT or PDF files. It is perfect for large scale projects, like when you're building a chatbot trained on a company's entire set of initial internal documents. So it also saves you from a lot of manual effort and ensures consistency across all your data sources. Now, this is where things get interesting, because not all data lives on your local machine. Sometimes the information you need is scattered across web pages, blogs, or online articles on the internet. And then that's where the web-based loader comes in. This loader fetches the data directly from a web page URL, extracts the text content, cleans it up, and then turns it into a usable document. So it's extremely handy for web scraping or live data retrieval. For example, pulling FAQs from a website, news content from an article, or product info from an online store. With web-based article, you're not just limited to static files. Your AI can now learn from live evolving web content from the internet. And finally, we have a CSV loader. So that's the one built for structural tabular data, like spreadsheet datasets or analytical reports. Instead of reading the file as raw text, CSV loader processes each row of your CSV file as a separate document, allowing the model to understand and retrieve structured information easily. Especially useful when combined with retrieval or Q&A components, where you might want your AI to answer questions like which product has the highest sales last month, or like who's the top growing employee, and then all sorts of stuff like that from a CSV based data source. So as we have completed these five document loaders, so each loader solves a unique problem here. First, text loader helps with plain text. PyPDF loader handles structured PDF documents. Directory loader manages bulk data. Web-based loader brings in dynamic online content, and CSV loader handles structured text. Now we're going to see the implementation of each of these loader in our code. Okay, so first of all, I'm going to create a folder. What is it? Number 9, and then call it document loaders. And then we'll start with the first one, which is our text loader.py. Okay, I'm going to create a few files here. Let's okay, for this we'll use the docs.txt file that we already have, and then we'll load this. Let me word wrap so that you can see the content of this, what it's written here. I'm not going to use the model. I'm just going to use the loader and then show you by loading the documents. So from LangChain_community.documentLoaders import text loader. Okay. Now you need to create a loader object from this text loader. So text loader, and then provide a file name, docs.txt, and then if you need to provide an encoding, you can also do it. So let's do it, encoding UTF-8. And then once you do this, you can print out your docs here. So first of all, let's do loader.load, and then you can print out your docs here. Okay, what did I do here? Let's exit this and then run this again. So as you can see, the content inside this docs folder has been loaded from my file here, and then the source is docs.txt. What you can also do is you can also see the type of this docs. So if you print the type of this docs, then you'll see that the type is list here. In the list, you have a document which encodes the metadata, that encodes source, and then inside the document we also have page content here. So you can directly also use this. So print docs 0 dot page content, which will directly print you the content inside the text that we have. Or you can also print out the metadata, docs 0 dot metadata, and then you'll be able to see the metadata, which is the source that we have. Okay, so this is our first loader that we have. Now we'll move to our second loader, which is our PyPDF loader. New file, so PyPDF loader.py. Here I'm going to copy a simple PDF file from somewhere and then paste it here. Okay, you can grab any PDF file that you want, and I'll go to PyPDF loader and I'll import from LangChain _ community.DocumentLoaders, import PyPDF loader. Now initialize the loader object, and my file name is dlcurriculum.pdf, so I'm going to use that same file name, curriculum.pdf. just a docs equals to loader.load, and then print out the docs. So whatever is present in this document will be loaded and then printed out. Okay, so we need to install PyPDF. So let's do this. PyPDF. Okay, and then type pip install. We'll just do PyPDF because everything else is installed here. And now that is installed, we can run our program again, which is PyPDF loader. Where is that? And you can see our PDF page content has been loaded, and it is loaded in the same format, which contains a list, and then that contains a document. Document contains some metadata inside this, and then along with that it also has its page content. So you can follow the same process as we did earlier here to print out the page content as well as the metadata. Okay, now we'll move to the third type, and then our third type is going to be our directory loader. So for that, I'm going to copy some PDFs inside a directory. So I basically have these AI books and a financial report, and then using this PDF inside this directory, I'm going to load the content of this particular books folder here. So let me open a new file and then call it directory loader.py. You can choose any kind of PDF inside a folder, and then that will work. Okay, so from LangChain community.DocumentLoaders, import directory loaders, and then we'll also do PyPDF loader because we have PDF content inside this. So loader equal to directory loader, and then we'll provide a path to this. So path is a folder called books, and then inside that I have contents like a file name .pdf, And then I'll also define a loader class, and my loader class is going to be a PyPDF loader. Okay, so what I can do is I can do loader dot lazy load, and then for document in docs, will only print the metadata here. So document dot metadata. Okay, let me clear this out and then run this again. So I have 4 different PDFs here, and for those 4 different PDFs, my document loader has started loading whatever it can find inside it. So since there is a lot of metadata that I have, so it has been loading every metadata it can find inside my folder here. So it's loading each and every page. That is why the metadata print is going on, but I think you understand what we're trying to do here. So I'm going to terminate this, and now we'll move to our fourth one, or our fourth loader, which will be our web-based loader. So let me create a new file, web-based loader.py. I'm going to import web-based loader from LangChain community .DocumentLoaders, import the web-based loader. Okay, now I don't need anything else. I'm simply going to copy a URL about a car review that I could find on the internet. So from this, I'll use loader equals to web-based loader, and then I'm going to pass the URL. Docs equals to loader.load, and then I'll print out the docs here. So this will open a website that contains a car review on it, and then I'm trying to load the text present in this particular URL here. So let me run this. Okay, so it also needs beautiful soup because it will I think go for web scraping of this. So we install PS4 or beautiful soup 4 here. I'll also mention it on the requirements.py. Okay, so since this is installed, so let me go and then run web-based loader again. Let me clear this and run this. It might take some time because scraping might take some time here, and then you can see that all of the text inside this are loaded, and then it's again in the same format. So the format is uniform. It has a list inside which it contains a document inside which we have metadata, and then there are a lot of other contents in the metadata as well, and then the page content actually contains the text content of that particular website. Now finally, I'm going to work on the last type of loader, which is a CSV loader. So for that, I'm going to paste a CSV file here on my project folder, so you can see the CSV file that I have. It's just a comma separated file that contains some data. You can use any kind of CSV file that you want. And now I'm going to go to document loader. I'm going to create a new file, 5 CSV loader.py. Okay, now again the import is the same from LangChain community. We import document loaders, import CSV loader, and then the loader is going to be an object of CSV loader. Inside this, I'm going to provide a file path. File path is going to be, what is my file name? So social network apps.csv. Let me rename this and then write data.csv so that it will be easier for me to write down the file name here. So data.csv. and data equals to loader.load, and then if I print data here, I will be able to see my CSV file content in this. Let me run this, and you can see it's again being presented in a similar format. Inside the list there is a document and there is a metadata, then inside it contains source and page number here, page content here. So this is how we use these 5 document loaders. This is an essential part of our retrieval augmented generation system, because on the very first step we need to load we need to load our data into our RAG system, which can be used as a knowledge base for our RAG project. So this is how we use it. I hope you understood the concept and also the implementation works for you. So imagine you're building an AI assistant that needs to remember everything you ever taught it, from long documents, research papers, or even notes scattered across multiple files. Now you wouldn't want your assistant to go through all those documents every single time you ask a question, right? It would be like asking a librarian to read every book in the library before giving an answer. And that's where VectorStore in LangChain comes into play. They're like the memory banks of AI system. So far in this LangChain journey, we've talked about how to load data and how to split it into smaller manageable pieces. We've also seen how to generate embeddings, those numerical fingerprints that represent meaning rather than just words. But once we have all those embeddings, we need a place to store them efficiently and a way to search through them intelligently. And that's what a vector store does. You can think of a vector store as a smart semantic database. Instead of storing plain text, it stores those high dimensional numbers, vectors, that capture the meaning behind the text. So when a new query comes in, the system converts it into an embedding too, and then compares it with the stored vectors to find the ones that are most similar in the meaning. So even if your query doesn't use the same word as your data, it can still find the right answer because it understands what you meant, not just what you said. So for example, if you ask who is known as Captain Cool, a traditional keyword search might not help unless that exact phrase exists somewhere. But a vector store the vector store understands that Captain Cool is semantically related to maybe Mahendra Singh Dhoni, because their embeddings are close to each other in vector space. That's the real power of vector database. They let your AI think in terms of meaning and not in terms of matching words. So in LangChain, we can use several vector stores like Faiz, Chroma, or Pinecone, among others. In our case, in this video, we're using Chroma, which is lightweight and works perfectly for local experiments. It stores all those embeddings persistently, so even when you restart your application, your AI doesn't forget what it has learned. And when you connect this to your retrieval pipeline, everything falls into place beautifully. The documents get embedded, stored in the vector database, and when a user asks a question, the system fetches the most relevant chunks. Not because of matching keywords, but because of the shared meaning here. So those retrieved chunks are then passed to your language model as additional context, helping it generate accurate and informed answers. So vector stores are one of the key reasons modern AI systems feel so intelligent. They make your assistant capable of remembering, reasoning, and retrieving information just like a human, instantly recalling the most meaningful pieces of information it has seen before. And without vector store, your AI would simply be guessing. And with them, it's reasoning based on the memory. So in short, we can say that vector stores turn static knowledge into searchable understanding, giving your AI a memory that's fast, scalable, and deeply semantic. So now let's go for the implementation of such vector store. Okay, so I'm going to create a new folder again here. Let's call this folder 11. Call it vector store. Okay, inside this, I'm going to create my first file, vectorstore.py. So let me use the LangChain Hugging Face embeddings. So for this part, so LangChain Hugging Face embeddings, let's also import Chroma, which is our vector database that we are going to use. So I don't think I've imported this. So let me install pip install LangChain underscore Chroma. And I'm also going to mention it on the requirements. So LangChain underscore Chroma. From LangChain underscore Chroma, import Chroma. Once it is installed, the error will then go. Okay, Chroma. Then we'll also import document. So from LangChain dot schema import document. Okay. I'm also going to load my Hugging Face credentials here. So from .env import load.env, and load.env function is called. Let me define my embedding model here. So I'm going to copy this from my previous code. So this model will be used as Hugging Face embedding. I think we've already used this in our previous code too, so this is not new for you. So here I'm going to create some document. Let me just copy these. These are too long for me to type. So I have some document related to some IPL players. So let me just copy this and then use word wrap. You can pause the video and then see what is being typed here. So now document 1 contains page content related to Virat Kohli and his team called Royal Challengers Bangalore. Document 2 is about Rohit Sharma and his team. Document 3 is about MS Dhoni and his team. Document 4 is about Jasprit Bumrah and his team. And then document 5 is about Ravindra Jadeja and his team. So these are the documents that I need to store in my vector embeddings. So here what I'm going to do is I'm going to combine all of this in a single list. So doc1, doc2, doc3, doc4, and doc5. Okay, now let me initialize my vector store. This will come from Chroma here. Chroma, and inside this I need to define my embedding function. My embedding function will be my embedding model that I've defined. My persist directory, let's just name it ChromaDB. A new folder called ChromaDB will be created in my project, and then my embeddings will be stored inside that. Then after that, I'll need a collection name. So the collection name will be sample. Now, since my vector store is initialized, and now I'm going to add my documents to the vector store. So vector store dot add documents, and then I'm going to add the collection of documents that I've created here. So what else? Let me retrieve vector store dot get, and then let me use some including words here. So embedding should be included whenever I retrieve from vector store. Document should be retrieved whenever I fetch from vector store, and then metadata should be retrieved. Okay, now I will have my query here. Let's say who among these are bowlers. So I have some players here, or cricket players. Among them, my query is who among these are bowlers. So what I'm going to do is I'm going to run a vector search. So vector store dot run a similarity search. My query will be my query here, and then I will fetch a top 3 result from this particular query. So, and then store everything in result, and then let's print out our result here. So let me run this. My documents will be embedded using this embedding model here, and then be stored in this vector database. And from that vector database, I will simply run a query and then run a similarity search in that query, and then get the relevant result here. So let me see. The first one, Mumbai Indians Jasprit Bumrah, is a baller. That's nice. The second one, Mumbai Indians Rohit Sharma, is also shown as a baller, and then the third one, Ravindra Jadeja, is also shown as the baller. So Virat Kohli and then MS Dhoni are excluded from these search lists, and then based on the similarity, it's found that Rohit Sharma, Bumrah, and then Ravindra Jadeja are ballers here. Let me also run another query here, if it's okay. We can also do something like this. So we can also print our result based on similarity search with scores. So if we see this, then we should see that the result Rohit Sharma should have a very low similarity score here. So similarity search with score. Okay, our query will be our query, and then we'll have a top 3 result here. So let me run this again. Then we should see that the similarity score for Rohit Sharma should be quite less than Bumrah or Ravindra Jadeja here, because Rohit Sharma is not in fact a bowler. Sometimes he does bowl off spin, but not much. So let's see. Okay, the first one is Jasprit Bumrah. So this is shown. Okay, okay, I've not printed the result. Let me also print the result. Let me omit the previous result, and then let me print it here. And then let me comment this out, and I just want to see the result with the similarity score. And then you might be wondering where this ChromaDB is. It should be well within here sometimes. So yes, you can see the folder called ChromaDB, and then using that particular ChromaDB vector database, my result is being pulled here. So Jasprit Bumrah has a similarity of something like 1.01. So again, it's saying Jasprit Bumrah, and then it's saying Jasprit Bumrah again. So the top result is only Bumrah, and then not the other bowlers here. So this is how VectorStore works. It converts our data or documents into embeddings and then store it, and then based on the query we have provided, we can fetch following contents, as well as what we can do is we can get the most similar result, or like run the similarity search on our given query against the stored documents. So I hope you understood the concept for VectorStore. It is just like a database, but instead of storing your data, it stores the embeddings of your documents. You've loaded a ton of documents onto your LangChain pipeline: PDFs, text file, web pages, you name it. But now comes the big question. How do you exactly find the most relevant piece of information when the user asks a question? And that's where the retrieval comes into play. Retrievers are like the memory search engine of your LangChain system. They don't generate new information. Instead, they fetch relevant documents from your existing knowledge base. So whenever a user query comes in, the retriever looks at all your index data and returns only the chunks that are most relevant to that query. In simple terms, think of retrievers as your AI's librarian. You ask a question and it doesn't hand you the entire library. It quickly finds the exact pages or paragraphs that matters the most. Now, under the hood, retrievers often work with vector stores. Whenever you add documents, they're converted into vector embeddings, numerical representation that capture the meaning of the text. Then, when a question comes in, it's also converted into a vector, and the retriever compares it with all stored vectors to find the closest matches. This is how your system ensures semantic relevance. It's not just matching words, but understanding the meaning. LangChain offers various types of retrievers. Some are simple keyword-based ones, others are embedding-based, and then others are even specialized ones like multi-query retrieval or contextual compression retriever that enhances retrieval quality using LLMs. Retrievals are essentially big or retrievers are essential because they bridge the gap between your static document and your conversational AI. They ensure your LLM has contextually rich, relevant data to reason with without needing to retrain or fine-tune the model itself. And in this video, we'll get hands-on with one of the most commonly used retrievers, the Wikipedia retriever, where we'll see how to pull real-time factual information straight from Wikipedia to enrich our AI response. So now let's go to the video. Okay, so I'm going to create a new folder again here. I'll call it, okay, what is the site? Okay, 12. So let's create a folder, 12 dot retrievers. I'll create a new file inside this. Let's call it Wikipedia retriever.py. Okay, so from LangChain community.retrievers import Wikipedia retriever. Then I'm going to define my retriever object here. So retriever object R equals to Wikipedia retriever. I'm going to get the top key results and then the language. I can also say the language, and then the language has to be English. So my query is, let's say, Indian Premier League. And then what I can do is I can use my retriever object to invoke this query. I'm not sure how many documents I'll find, but let's print out the length of the document that I'm going to find here. So length docs. Let me run this. Okay, so I need to install Wikipedia. So let's go to a requirement, add a new library, save it. I'm directly going to install this without going to the requirements.py or other requirements.txt. So let me rerun this again. Where is that? Wikipedia retriever, yeah. So let me run this. It will take some time because it will again go to Wikipedia and then get the results from there. So yeah, this is my since I've only asked for top 2 results, so it is giving me 2 results, and then for this one I can print each and every of my results. So for idoc in enumerate docs, what I can print is the results. So f result I plus 1, and then print content, and inside content I can print dot page content. Okay, so if I print this again, I will have my 2 documents as well as its content too, and then that is straight from some Wikipedia pages about this particular topic here. So this is how we use retrievers. In the next video, we'll see something else, or like we'll see more in the retriever section, and then we'll also use it on the local data or local documents. In the last video, we explored what retrievers are and why they are such an essential part of LangChain. Now let's see how they actually come to life with the help of something called a VectorStore retriever. Think of a VectorStore as a smart database that doesn't just store text, it stores the meaning. We've already talked about this. Every sentence, paragraph, or document we feed into it is converted into a numerical representation called an embedding, and then these embeddings capture the semantic meaning of our text. So instead of searching for exact words, a retriever searches for similar ideas. So in this video, we're using Chroma, which we've already used earlier, which is one of the most popular open source vector databases out there. So once we add our documents into Chroma, it handles all the heavy lifting, storing, indexing, and efficiently searching through our vectorized data. Now to generate these embeddings, we'll be using Hugging Face embeddings, a special model that we've already used in the past. The model will transform each document into a high dimensional vector allowing Chroma to understand the relationship between different pieces of text. And then when we convert our Chroma vector store into a retriever, what we're really doing is giving our application the power to search semantically. So when we ask a question like what is Chroma used for, it doesn't just look for that exact phrase, but it finds sentences that mean something similar even though they're using different words. So the combination of Hugging Face embeddings and Chroma retriever forms the backbone of the retrieval augmented generation RAG system that we've been talking about, and then a simple form of RAG we've already implemented in a previous video. So by the end of this video, you'll see how this retriever transforms ordinary text into a scalable, intelligent knowledge base that your AI can reason over effortlessly. Now, without any delay, let's go to the code. So I'm going to delete this Chroma database for now because it already contains previous embedding. So I'm going to create a new file here inside retrievers and then call it VectorStore retrievers.py. So let me import Chroma first. So from LangChain _Chroma, import Chroma. From LangChain _Hugging Face, import Hugging Face embeddings. From LangChain _core.documents, import document. Okay, so I'll also need to load .env. So from .env import load.env. Let me do load.env, load the Hugging Face credentials here. I'm going to create a document. I'll just copy paste it from somewhere. So these will be my source documents here. Let me wrap this up. Okay, so these will be my source documents here. We have these four contents each defined inside a document. Then we'll initialize our embedding model. So this will be our Hugging Face embedding model. We'll use sentence transformers and then a model inside this sentence transformer. So what we're going to do is we're going to create a vector store. We've already done this again, so we'll use Chroma .from documents from _ documents. So our documents will be the document that we have here. Our embedding will be the embedding model that we have, and then the collection name let's say will be the sample. Okay, now we'll convert our vector store into a retriever. So a retriever equals to vector store dot as a retriever. I just need to pass the search keyword arguments. Search quarks equals to let me pass a dict here, so equal to 2. So I'm basically getting a top 2 result here. So query equals to, let's ask about embedding. So what does embedding do? And then based on this, I'm going to invoke my result. So retriever dot invoke, and then I'm going to get query, and based on this I'm just going to print the result whatever it throws at me. So now let's run this. We have used vector store as a retriever here. Let's run this and then see what happens. So all of these are being converted to embeddings, and then a ChromaDB database is being created, and along with that it is being converted to retrievers. It is being converted as a retriever and then giving me the result. So if you see here, what I can see is whenever I ask about embedding, it gives me this result at first and then the embedding result. Do I have an embedding result? No, I have this Chroma, and then also I have this LangChain result here. So I have these three documents provided to me for this particular question here. Or let me change my question and then ask, what is Chroma used for? And I just need one result here. Let me mention it to one and run this. So again, as you can see, my search directly redirects me to this. Chroma is a vector database optimized for LM search. It also provides me some more answers, few more answers here related to embeddings and then the OpenAI, but my most relevant result is the particular document here, or this particular document here for the query here. Okay, so this was another type of retriever that we've used. In this video, we're going to bring together everything we've learned so far, from document loaders and text splitters to embeddings, vector stores, and retrievers, and use them to build something real. Imagine being able to ask questions directly about the content of any YouTube video without manually watching or scrubbing through it. That's exactly what we're going to do. We'll start by pulling the transcript of a YouTube video using the YouTube Transcript API. This gives us all the spoken text, which then becomes the foundation of our knowledge base. Now, we'll use a recursive character text splitter to break that long transcript into manageable chunks, so our system can process and retrieve information efficiently. Then comes the magic. We'll convert those chunks into embeddings using a Hugging Face model and store them in a FIAS vector database. This allows our system to search and retrieve content that's semantically related to any questions we ask. Once that's done, we'll turn FIAS into a retriever, which will find the most relevant parts of the transcript related to our query. Finally, we'll use a Gemini Flash model, Google's powerful language model, to analyze that content and generate an accurate transcript-based answer to our question. In short, we're transforming a YouTube video into an intelligent, searchable knowledge source. By the end of this video, you'll understand how all the individual LangChain components like loaders, splitters, embeddings, retrievers, and models come together to create a fully functional question answering pipeline powered by a real video content. So let's go to the implementation. So I'm going to create a new folder again. Let's call this Rack Systems. And inside this, I'm going to create a new file, YouTube_rack.py. Okay, first of all, I'm going to pull up YouTube Transcript API, import YouTube Transcript API and transcripts disabled. We'll need to install this library here because once I try to run this, so we'll need to install YouTube Transcript API. So let me just do pip install YouTube Transcript _API. Okay, done. I'm going to import a recursive character text splitter here. After this, embedding from our Hugging Face models. Then we'll import our model. I'll also import the prompt template. Then I'll import the vector database. And then finally, to load our credential, I'll import load.env. So step 1 is indexing or our document injection. So I'll take a video ID, and for video ID, I'm going to take my own YouTube video here somewhere. Let me also load this credential, and let's go to the video ID part. Okay, so here is our video on like building a RAG pipeline, which we did a couple of days earlier in video number 17. So I'm just going to copy this particular video ID from the URL and then paste it in my code. Okay, so this is going to be my video ID. Then what I'm going to do is I'm going to try and then I'm going to initialize an object of YouTube API or YouTube transcript API, and then I'm going to pull my transcript here. So yt_api.fetch. My video ID will be my video ID, and then the language of the video is English. I want transcript in English. Then I'm going to flatten the transcript to plain text. So for this, what I'm going to do is transcript equals to dot join chunk dot text for chunk in transcript list. We'll also put an exceptions here. So if transcripts are disabled, then we'll say no captions available for the video. Okay, so this is step 1. We'll move to step 2. In step 2, we'll do indexing, which means our text splitting. So for that, we already have our splitter here. So let me initialize the object of the splitter. So splitter equals to recursive character text splitter. I'm going to define a chunk size of maybe 1000, and then a chunk overlap. Okay, we'll not do 1000. 1000 is too long. So we'll do a chunk size of 300, and then a chunk overlap of 50. And then I'm going to use the splitter to split my text here or split my transcript. So create documents, transcript. If you want to see how many chunks we've broken it down into, so let's see if we can indeed extract the captions or transcript from our video or not. So let me run this. Okay, so we have 33 chunks. We could extract the transcript from our video. So let's go to step 3. The step 3 is embedding generation and storing in vector database. Okay, so embedding model will be used from Hugging Face Embeddings, and then the model name is sentence transformers all mini LM L6 v2. The model I found it from our Hugging Face library. Let's also initialize our VectorStore. So VectorStore is done using files. So from documents chunks, and then embedding equals to embedding model. Okay, so next is retrieval. Retriever. So I'm going to create my retriever from my VectorStore as a retriever, and then the search type is going to be based on similarity, and then search keyword arguments. Let me do this again. So search underscore keyword arguments is equal to the top, let's say, two results here. Okay, let me design my prompt using my prompt template. So in case of prompt template, let me define my template here. So let's provide you are a helpful assistant. Answer only from the provided transcript context. If the context is insufficient, just answer I don't know. And then let me add a line break and then mention context is equal to context, and question, another line break, question is equal to question. Okay, so this will be my template here. I don't think I need to put an F string, so let me remove this. So input variables are context and questions. Context and question. Okay, so this is done. Now let me devise my question here. What is the video talking about? And then we'll also join a context text. So context text is going to be joined from let's do this, /n dot join dot page underscore content for doc in retrieved docs, and then retrieved docs is going to be retriever dot invoke question. Okay, so after that, I'm going to create my final prompt. So final prompt equals to prompt dot invoke. I need to pass two variables. One is the context, which I can provide from context text, and then the other is the question, which I can provide from my question here. And finally, I can invoke my model. So model dot invoke final prompt. I've defined my model, right? Okay, I've not defined my model, so let me also define my model here. So model equal to chat Google generative AI. Model equals to Gemini 2.5 Flash model, and then print answer dot content from here. So let me run this and then see if we can actually get the answer from our generated transcript or not. Let me remove this print statement for now and then run it. I missed a comma. Let's see. Yeah, I should have provided a comma here at the end of the text. So let me run it again. It will take some time for transcript generation as well as the embedding model loading, and also it will take some time for the retriever to work here. So at first the model is being downloaded. I think I've already used this model earlier. I might have changed something here. Let me check. Okay, so yeah. Okay, so model was downloaded. So the video is talking about using embeddings to make a model retrieve and reason over real data. It will build a simple retrieval augmented generation. Okay, it works. In fact, we're talking about the FICE model in that particular video. And then it works. So I'll pass something that is not present in the context. So I'll pass this question here. My question will be, does the video, or like, what does the creator say about Brazil in the World Cup football? I don't think the context for this is present in the video, so the model should say that it simply doesn't know about it. Let me run this again. It would be efficient to just store this transcript locally once it is downloaded, so that every time the transcript fetching part is not done, as well as the vector store can also be stored. So as you can see, for this question, what does the creator say about Brazil in the World Cup football? It simply says, I don't know, because that particular context is not present in our transcript. So this is it. We have successfully implemented a YouTube transcript knowledge base, and then from that created a retrieval augmented generation system answering our particular question. So I hope it runs on your end too. In the earlier videos, we've used language models in a very traditional way as chat-based systems. You'd give them a prompt, they'd generate a response, and that was it. But now things are evolving. The new wave of this agentic AI isn't just about generating text. It's about actions. Models are no longer limited to just answering questions. They can now call functions, interact with external systems, and even perform real operations on the behalf of user. This is where tools in LangChain comes into play. Tools act as a bridge between the reasoning power of an LLM and the functional capabilities of your code. Instead of the model telling you what to do, it can now do it by invoking the right tool. Imagine this. You ask an AI, what is the product of 5 and 9? So instead of reasoning through the multiplication itself, it recognizes that there's already a defined tool that can perform this exact task and call it automatically. This shift is massive because it transforms LLM from being just text generators into decision-making agents. They can analyze context, plan what needs to be done, and then use the appropriate functions to get accurate results, all autonomously. In this video, we'll explore how to define and register tools in LangChain using the tool decorator, which turns ordinary Python function into callable AI tools. And by the end of this video, you'll understand how this small but powerful addition lays the foundation for building LLM-powered agents that can think, reason, and act, not just chat. So let's go to the implementation. So again, I'm going to create a new folder. Folder 14, and then name it tools. Inside this, I'm going to create a new file, tools.py. So here, first of all, from LangChain core, I'm going to import tools. So let's create a function here. So our function will simply be a def multiply function. Def multiply a comma b, and then this will result into a integer, or I'll also define it in this way. So a is supposed to be an integer, b is also supposed to be an integer, and then the product, or whatever this does, should return an integer here. So A into B. Also make sure to include the doc string that actually defines what this function does, because that is important here. So let me write multiply two numbers and then incorporate this using the @tool decorator. Okay, now this is not just a normal function, but it is a LangChain tool function here. So now what I'm going to do is I'm going to invoke this multiply function, multiply.invoke, and then simply pass equal to 3 and then b equal to 5. So now also this should be passed within our curly brackets. So let me provide it in that way. And then what I can do is I can print out the result. Now you can see that this particular tool will be invoked, or the tool will invoke the following values and then return our multiplication result here. So let me run this, and it's pretty easy. 5 into 4 is equal to 20. So this is how you do it. You can also see the function name here. You can also see what the doc string in the function says. Doc string and then you can also see what arguments you need to pass inside this particular tool. So let me run this again, and then you can see that the function name is multiply. You can also see this doc string for this second line here, and then the argument you need to pass is a variable a, which needs to be an integer, and variable b, which also needs to be an integer. What you can also do is you can also see the argument schema in terms of JSON. So for that, model underscore JSON underscore schema. Run this again, and then you can see everything that we have talked about here in the form of a JSON schema. So this is just a basic introduction of using tool in LangChain. In the further videos, we'll explore how we can integrate this with LLM2. In the last video, we saw how the tool decorator helps turn a simple Python function into a callable AI tool, something our language model can recognize and use when reasoning. But what if we want more structure and control? What if we want to clearly define the input parameters, their types, and even attach rich detail for each, making the tool more transparent and reliable for the model to use? That's where the structured tool comes in. Structured tool takes the concept of tools a step further. It lets us wrap a function with a Pydantic model that defines exactly what inputs the tool expects. That means every parameter has a type, a detail, and validation rules, ensuring the LLM knows precisely how to use the tool. Think of it like giving the model a manual. Instead of saying, here's a function, good luck figuring it out, you're saying, here's a tool that multiplies two numbers. It requires exactly two integers, a and b, and here's what they represent. This structured approach becomes incredibly useful when you're working with multiple tools or building complex agentic agents. It reduces ambiguity and helps the LLM call your tools correctly every time. So in this video, we'll explore how to define a structured tool using StructuredTool.from function, how to specify input schemas using Pydantic, and why this approach is considered the more scalable and professional way to build tools for LLM agents. So let's go to the implementation. So here I'm going to create a new file again, and then call it StructuredTool.py. Here I will have LangChain. From LangChain.tools, I'm going to import structured tool. And then from Pydantic, I'm going to import base model and a field. Okay, so I'll first define my Pydantic class here. So multiply input. This will import base model here, and then I'll have two parameters. A, which will be an integer. I can write a field for this one, and then details of this particular field. So description equals to the first number to multiply. I'll also say this is a required value. So required equals to true. And then similarly, I'll have the second number here. Let me call this second number to multiply, and then write B here. Now, what I can do is I can define the multiply function. Multiply function, A will accept an integer, B will also accept an integer, and then we'll also return the integer. So I'll go return A into B. I'll define my multiply tool using the structured tool function dot from underscore function, and inside this I'm going to write my function name, which is multiply function. Then I'm going to provide a name to this, which is multiply. Then I'm going to write a doc string for this. So multiplies two numbers, and then provide the argument schema, and the argument schema is based on the Pydantic class that we have, which is multiply input. Okay, now after this, what I can do is I can invoke this structure tool, multiply underscore tool dot invoke. Then I can pass in the two values. Let's call A equal to 5 and B can be passed as 4. And from this, I can print out my result. And then run this again. So in our previous video, what we had done is we had used the tool decorator to define the tool function, but in this case we've defined a Pydantic class for validation too, and then we have used structured tool to invoke this particular function here, which follows the validation rules provided in this Pydantic class. So I hope you understood the concept and then the major difference between tool and structured tool in LangChain. So far, we've talked about how to create individual tools, simple functions that an AI model can understand, interpret, and use. But in real-world application, we rarely rely on just one tool. Think about it. An AI assistant might need to add numbers, search the web, analyze text, or fetch data from a database. Each of these capabilities is a separate tool. And when you have several of them, it makes sense to group them inside a toolkit. So a toolkit in LangChain is simply a collection of related tools bundled together, usually around a specific purpose. For example, you might have a math toolkit for arithmetic operation, or database toolkit for interacting with SQL or MongoDB, or a web toolkit for scraping and browsing data. Toolkits make your code modular and organized. Instead of handling each tool individually, you can register, manage, or pass around entire group of tools as a single unit, especially when integrating them with agents. It's like giving your AI a toolbox instead of just one wrench. Now it can pick the right tool for the right job. In this video, we'll explore how to define a simple toolkit in LangChain, how to group multiple tools inside it, and how this concept becomes the foundation for building intelligent, multi-skilled AI agents that can reason and act automatically or dynamically. So let's move to the code. So I'm going to create a new file here called toolkit.py, and inside this I'm again going to import tools, LangChain underscore core dot tools, import tool, and then in our decorator what I'm going to do is I'm going to create two tools here. So one will be for addition, which will contain two parameter, an integer. B will also be an integer, and then it will also return an integer here. So return A plus B. I want to include something in the doc string to here, and this will say add two numbers. Similarly, I'll have another tool for multiply, and then it will also take in two numbers, integer, b is also integer, and then it will reply or return an integer itself. I'll have a doc string says multiply two numbers, and then it will do return a into b. Okay, so I have multiple tools implementation here. So what I'm going to do is I'm going to define a toolkit here called Mac toolkit, and then inside this I'll have a get tools function, which will contain a self keyword, and it will return add and then multiplication here, a tool here. Okay, then what I'm going to do is I'm going to create a toolkit object of this Mac toolkit class, and then inside this I'm going to get my two different tools using this toolkit. So get tools, and then I'm going to print each and every tools here. So ptl in tools, let's print out the name of the tool, so tl.name, and then what we'll do is we'll also print out the detail of this tool. So tl, and then the detail will be tl.description. So if you run this, you'll see that we have bound these two different tools. Okay, something's wrong here. Let me check what I've done. So I've defined a class. I've also defined an object for the Mac toolkit class. Okay, the object definition is wrong here. So let me run this again. And then using this toolkit class, I can get a list of all available tools that I have. So I have two tools here. One is for add, and then the other is for multiply. So if I need to add one more tool here, let's add one more tool called sub, which will take in a and b. Both are integers for now. It will also return an integer, and I'll include a doc string subtract two numbers, and inside this I'll return a minus b, and then I'll also include this tool here for sub. Then again the toolkit wraps all of my tools, and then it gives me a choice to choose one among all of these tools here. So this is how you implement toolkit. So I'm ending this video right now. I hope you understood the concept. We'll further work on tools and then integrate it with LLMs in the upcoming video. Up until now, we've seen how tools can be created and grouped into toolkits. But what if we want our AI model to actively use those tools during conversation? That's where tool binding comes in. So tool binding is the process of connecting your AI model directly with one or more tools, so the model can recognize when a tool should be used and even suggest calling it with the right parameters. Essentially, the model becomes aware of the tools it has. So this is a critical step towards agentic AI, because now the AI isn't just generating text. It can reason about actions and leverage external functionality to get things done. So for example, instead of manually calculating a sum or querying a database, the AI can now identify the need, prepare the inputs, and suggest invoking the relevant tool. It's important to note that in this setup, the model itself doesn't execute the tool. It only proposes a tool call, complete with arguments. The actual extension is handled programmatically, giving developers control over safety, validation, and workflow. So in this video, we'll focus on binding a tool to our LLM, seeing how the model suggests tool usage, and then executing the tool's action based on the model suggestion. This is going to be a crucial step toward creating intelligent agent that can work or that can do tasks beyond just generating text. So let's go for the implementation. So here I'm going to create a new file called a tool binding.py. Let's import tool. So from LangChain core, LangChain_core.tools import tool. Okay, what else do I need? We'll import our model. So from LangChain Google Gen AI, import chat Google Generative AI. And then I'm going to load my credential from .env, import load.env. So let me first load my credential. Let me then load my model. My model name is Gemini 2.5 Flash model. Let me create a tool here. So my first tool here is add, which will take in two numbers a and b. Both will be integers, and it will also return an integer value. I'll add a docstring to this. So adds two numbers, and then I will return a plus b here. Okay, so this is done. The tool import I think is wrong, so it should be small tol tool. What else? Okay, with just one tool, we'll try to bind this with LLM. Okay, so LLM with tools equals to model dot bind tools, and then I'm going to bind my tool into this. So we can see invoking a query with this particular LLM, which contains tools here. So let's invoke this, and then we'll say, can you add 3 with 14, and then basically see the result here. Or what I can do is we'll first print out the result and then we'll see it accordingly. So if we print out the result, then the model will not itself start doing the computation, but it will look at this particular query and then the docstring, and then based on the similar docstring with the query, it will understand that now this tool needs to be called. Okay, let's run this and then you'll get a clear picture of what I'm trying to say here. So if we run this, so as you can see, the content is actually not an exact answer, but it is a tool call here or a function call. So it says function call, and then the function name here is add. The arguments are a and b, and then 3 and 14 are passed to a and b here. And then what the model is suggesting is, it is suggesting me to call this particular function or call this tool to perform the task that is mentioned in the query instead of the model doing the computation itself here. So this is how we bind the tools. And then the model, like I said earlier, the model does not itself call the tool, but it actually provides you the suggestion to the user that this particular tool can be called to perform this particular task that is asked to do here. Up until the previous video, we explored tool binding, where the AI could suggest using a tool, but it didn't actually execute it. That's a big step towards agentic behavior, but it still required a human or programmatic step to run the tool. In this video, we're taking it one step further. We're going to enforce the model to actually perform the tool operation as part of the workflow. This means the AI isn't just suggesting, it can now actively interact with tools, gather results, and continue reasoning based on those results. The process works like a conversation flow. First, the user provides a query. The model, aware of the tools, chooses which tool to call and then prepares the arguments. Next, we execute the suggested tool call programmatically, and finally, the model gets the tool's output and integrates it into its response, allowing it to continue the dialogue seamlessly with real results. This approach is critical for building truly intelligent agents, one that just doesn't answer questions but can perform tasks or compute results or fetch data dynamically. So in this video, our focus will be on implementing this enforced tool execution workflow. The model identifies the tool, we run it, and then the AI incorporates the output back into the conversation, making the interaction fully functional and autonomous. So let's dive into the code. So here I'm going to create a new file again. Call it final tool calling.py. Let me import few libraries here. So from LangChain core dot tools, I'll import tool. Then from LangChain core dot messages, I'll import human message. Then I'll import my model. And after that, I will import .env. Okay, now I'll import the credential, then I'll define my model. Chat Google Generative AI. So the model name is Gemini 2.5 Flash. And then I'm going to create a tool for basically addition like we did in the earlier video. So def add, A is going to be an integer, B is also going to be an integer. And I will return the result as an integer. I'll add a docstring, add to numbers. And then based on this, I'm going to return A plus B. Now I'll bind this tool. So LLM with tools equals to LLM dot bind tools, and I'm going to bind my add function tool here. My user query is going to be can you add 10 and 9. Okay, and then I'm going to convert this into human message. So my query is a human message. So we'll append this in our message list, our query now, and then we'll print our result. Basically call the LLM using our messages and then print out the result. We'll see the result, what happens here. Okay, so if you run this, you'll see that it does suggest a function call here for add to basically solve my query. So what I'm going to do here is I'm going to append this same to my messages. So messages dot append, it will go inside here. Also, I want to print something here. So let me print out result dot tool underscore calls. I think we have tool calls here. Yeah, we have tool calls here. So tool call, and then we'll invoke our first tool call and see what it gives me. So let me run this again. So if we print tool call, then we can see that this particular tool is a reference, or the add tool is a reference. My values are correctly gone to A and B. So now what I'm going to do is I'm again going to remove this, and then I'm going to invoke the tool add.invoke result.tool underscore calls 0. Then after this, I'm going to append the tool result also inside my messages, and then the final result will be the LLM call again dot invoke, and then I'll print my final result here. So print final underscore result. So let me clear this and then run this again and see what happens. Okay, as you can see, the sum of 10 and 9 is 19. The content is generated. If you only want to see the content, then you can see that the content is shown. Okay, so what we did here is we did in fact invoke the tool, but we did it by ourselves. So basically we took the model suggestion of invoking the add tool, we invoked the add tool, and then basically regenerated our response based on our query here. That's not actually what we want, but I actually wanted to show you how to call the tool here. In the upcoming video, we will fix this, and then we will let the model suggest the tool as well as call the tool automatically here. So I think you understood the concept. In our previous videos, we explored how an LLM can suggest tools and how we can execute those tools manually. But what if we want the model to actually carry out a multi-step workflow, handle immediate results, and inject critical information into subsequent tool calls automatically? And that's where the concept of injected tools comes in. And it's what we're exploring in this video. So imagine the LLM as a helpful assistant with access to a set of tools, like a calculator or a currency converter. When you ask it a question, it might realize that to answer fully, it needs to use more than one tool in a sequence. For example, if you ask like what is the conversion factor between USD and NPR, and based on that, can you convert 10 USD to NPR, the assistant first needs to fetch the conversion rate and then apply that rate to the value you want to convert. The magic happens through injected tools arguments. This tool allows the LLM to recognize that some tools require additional input, like the conversion rate for this case, which might not be explicitly provided by the user, but is generated by a previous tool call. Essentially, it allows the LLM to remember and pass context between tool executions automatically. And here's how the workflow unfolds. First of all, we start with the LLM call. So we send the user's query to the LLM bound with tools. The LLM analyzes the query and chooses which tools need to be executed. For instance, it first calls the get conversion factor tool and then plans to call the convert tool. The second is the multi-turn tool execution loop. Here, the code then executes each suggested tool. When the LLM calls convert, it might not know the exact conversion rate yet. This is where the injected argument comes into play. The program automatically injects the conversion rate obtained from the previous tool call, ensuring the tool has all the information it needs. And the final is the feedback or feeding results back to the LLM. So after each tool execution, the result is packaged into a tool message and then sent back to the LLM. The LLM then uses these output to generate the upcoming step or finalize its response. The loop continues until LLM produces a final human readable answer in the content field. So this approach is powerful because it transforms the LLM from a simple chat model into a true agentic system. It can now plan, execute, and chain multiple operations together while intelligently handling dependencies between them. So in this video, we will walk through a live implementation of this workflow. We'll see the LLM first retrieve the conversion rate and then use it to convert a currency amount, and finally produce a complete readable answer for the user, all automatically. So this pattern is not only limited to currency conversion, it's a blueprint for like building multi-step AI agents that can handle complex tasks with multiple tools and dependencies. Now let's move on to the implementation. So I'm going to create a new file here, call it test multiple tool call.py. Okay, so inside this, first of all, the imports. First import tool. After that, import tool message as well as human message. Then load the model. then a .env. Here from inside LangChain to LangChain core .tools, I'm also going to add InjectedTool arg, and then last one from typing, I'm going to import annotated. Okay, so first of all, load the credentials. Then I'm going to define a tool here. So this tool will be get conversion rate. It will contain two strings. One is base currency. It will be a string, and then the other is target currency. It'll also be a string, and then it will basically return a float value. So write something in the doc string, return the real-time currency conversion rate from base currency to target currency using some API. And here I'm actually not going to call the API, but I'm directly going to use this static conversion rate. Let's say 140.3. Okay, and then I'm going to return this conversion rate from this tool. Next, I'm going to create another tool here that is going to be named as convert. Here I will have a base currency value, which will be in float, and then I'll have a conversion rate which will also be in float, but it will be annotated, and then float and InjectedTool arg. Basically, first of all, the value will come from the other tool to this particular tool here, and then it will also return a float value. Write a doc string, converts a base currency value into target currency value using a conversion rate. Okay, so this is going to return base currency value into conversion rate. Now we will set up LLM. So LLM equal to Chat Google Generative AI. The model is going to be Gemini 2.5 flash model. Then what I'm going to do is I'm going to bind these tools. So LLM with tools equals to LLM dot bind tools. The first tool is get conversion rate, and then the second tool is convert. Now I'm going to pass in my query. So my query is going to be, what is the conversion factor between USD and NPR, and based on it, can you convert 10 USD to NPR? Okay, so this is going to be my query here. Now, what I'm going to do is I'm going to include this query as a human message where the content is going to be query, and I'm going to wrap this up in a list itself. Okay, so let me invoke the tool and then get the AI message from this. So LLM with tools dot invoke messages, and then whatever I get, I'm going to append it in the messages itself. So append AI underscore message. Okay, now in step 2, we go for multi-turn tool execution loop. So while AI underscore message dot content equals to an empty string, and AI underscore message dot tool calls tool calls. So if something is present in the tool calls, what I'm going to do is I am going to create a list of tool messages, and then based on this, I'm going to execute all suggested tool. So for tool call in AI_message.tool calls, I'll first call in the tool name, which is going to come from tool call name. I will also try to get its ID. So tool ID equals to tool call ID, and then I'll get the arguments. So tool args equals to tool call, and then args here. Okay, so let me print every tool that I've got. So executing tool, and here will be my tool name with args, and then here will be my tool args. So this will be made as an f string here. Okay, this will be, or I can just do this, and then this is going to be my f string. So now if the tool name is equals to get conversion rate, then I'll invoke that function here, .invoke, or invoke that tool, and then I'll get the tool output in the form of a string, and then that will be my conversion rate. So else, if the tool name is equals to convert, so if the tool name is directly convert, then what we need to do is we need to first inject the conversion rate from the previous result step. So if conversion rate not in tool underscore args, ensure the conversion rate is actually defined from the get conversion factor run. So if conversion rate not in locals or conversion rate is none, then what we need to do is we need to raise our value error saying that conversion rate is required but is not found. Else what we need to do, we need to get the conversion rate from tool args, conversion underscore rate equal to conversion rate. And then based on this, I need to execute my tools. So converted value equals to convert dot invoke tool args, and then tool output can be converted to a string value using str function. Okay, if none of this is possible, we'll do tool output equals to unknown tool, and then we'll say tool underscore name. Okay, most of our work is done. What we need to do is now we need to, since every condition returns a tool message to us, so what we're going to do is we're going to create a tool message. It will be wrapped inside this tool message here. The content is going to be tool output, and then the tool call ID will come from the tool ID. And I'm going to append tool messages dot append tool message tool underscore msg, and then now I'm going to append everything to our messages here. So still, I mean, I am supposed to be inside this loop here. Okay, I think I did some mistake here. So this has to go inside the while loop. Inside the while loop, and then now what I'm going to do is I'm going to messages dot extend or append it. You can use anything, tool messages. Then I'll again prompt for AI message and then invoke the model with the updated messages, and then I'm again going to append it in my AI message. Okay, so finally we already should have obtained our result inside this particular part here. So what I'm going to do is I'm going to take out the last result. So messages -1, and then I'm going to print the final result dot content. So let's see. My query is, what is the conversion factor between USD and NPR, and based on it, can you convert it from 10 USD to NPR? So if you run this, let's see what happens. So the model is called, the model is initialized. So okay, the conversion rate between USD and NPR is 140.3. This is done using this get conversion rate tool, and then from that, after that, we call this convert tool with the base currency value of 10, and then the exchange rate or the conversion rate of 140.3, and then 10 USD is equivalent to 1403 NPR. So this is the result. So here we've not only integrated multiple LLMs multiple tools into an LLM, but we've also used this concept of injected tool, where the result of the previous tool will be the input for the upcoming tool. So I hope you understand the concept of injected tool, and then you had fun implementing this particular code here. If you have any problem, do comment down below and I'll try to help you out. And in the next few videos, we're going to see AI agents demo using LangChain. So we are almost at the end of this LangChain series here. Hello everyone, and welcome back to the channel. So far, we've done our LangChain series. If you haven't watched that, I'll put a playlist link down below, and then you can check it out. And in that LangChain series, we've learned how to build LLM-powered applications step by step. We have explored chains, agents, retrievers, and even tool execution. We saw how LangChain helps us connect large language models with external data sources, APIs, and other tools. But as we started building more complex systems, you might have noticed something missing. LangChain is actually great for creating individual components. But when you try to build multi-step workflows or systems where an LLM needs to make choices dynamically, things start getting a bit messy. You have to manage the control flow manually, handle intermediate steps, and sometimes even patch the logic together with if-else conditions. It works, but it's not scalable and it's definitely not elegant. So that's exactly where LangGraph comes in. LangGraph takes everything we've learned from LangChain and gives it a structure. It lets us represent our LLM workflows as a graph with nodes for actions and edges for choices paths. In simple terms, it's like giving our agent a map to follow, so it knows what to do, when to do it, and how to handle intermediate results. With LangGraph, we can build stateful, reliable, and controllable AI systems, where every step is transparent, and the workflow is easy to debug, modify, or extend. So if LangChain was all about learning the tools, LangGraph is about learning how to orchestrate them intelligently. And that's exactly what we're going to do next. We're starting a brand new series on LangGraph, where we'll go from the basics all the way up to building advanced multi-step agentic workflows. So get ready, because if you loved what LangChain could do, LangGraph is going to take things to a whole new level. So let's get started. In the last video, we talked about why we're moving from LangChain to LangGraph, and today we're taking our very first step into it. So imagine you have a chatbot that takes some input, let's say a name, and then it needs to process that information step by step before giving a response. So in LangChain, we'd probably just call a function or a chain directly, but in LangGraph, we think differently. We treat our program as a graph, a flow of states moving through connected nodes. Each node represents a specific action or step, and the state carries data as it moves through those steps. In the example that we'll be doing, our state is just a collection that holds a single key, which is messages. Think of it as a small memory that keeps track of whatever our chatbot knows at the moment. Then we will define a node, a simple function that takes this state, modifies it by adding a friendly greeting, and then returns the updated state. That's all a node does. It only transforms data. Next, the graph connects the dots. So we say when the process starts, go to this node, execute it, and then end the process. It's like drawing a mini flowchart. Start, then do something, and then end. So when we run it, LangGraph automatically handles the execution. It passes the state through the node, updates it, and gives us the final result. The output you see isn't just a printed message. It's the outcome of data flowing through structured logical graph. And that's the beauty of LangGraph. You're not just writing code anymore. You're designing a process. A process that's visual, controllable, and scalable. So in the upcoming videos, we'll slowly build on this foundation, adding more nodes and more edges, and eventually intelligent choice making to our graph. So stick around, because this simple example is just the beginning of how LangGraph turns logic into flow. So let's go to the example now. So I'll be creating a new folder here, and then I'll call it LangGraph. And then inside this, I'll create my first file. So basic graph.ipynb. We'll do this in the notebook format here. Okay, so first of all, I need to install LangGraph here. So LangGraph, let me run this. And then once LangGraph is installed, we're ready to build our first graph here. So from typing, import typed dict and dict dict. We'll run this and then select the interpreter here. Python environments, and then our recommended interpreter is this one. So as you can see, it can run the interpreter. Okay, I'd also like to import from langgraph.graph, import state graph, start, and then end. Okay, this is going to be our first import here. Okay, our first cell is running. Now I'd like to create a class called my message state, which will have a type dict as inside it. So inside this, I'll have a simple message that will be in the string format. Then after this, what I'm going to do is I'm now going to define my graph directly here. So my graph will be from state graph, and then inside this I'm going to pass my class that I've just created. So I'll add nodes to this graph. The first node will be we need to provide a string name to this, let's say initial, and then provide a function here. So greeting node. Okay, so this particular function needs to be implemented on top of this. Let's write down this function greeting node. This is always going to have this parameter of this class that I've just created. and then it is going to return the same class that we have. Now, okay, what does this do? This is a simple node that adds a greeting message to the state. Okay, so let me write state, or basically update the state here. So up until now, this is all empty. Now I'm updating this. So I'm writing hello hello plus state message, whatever we have in message, plus and then maybe give full stop and welcome to LangGraph. Okay, so this is going to be my function, and then I've already added it as a node in my graph here. So we only have one node for now. Now we're going to add edges to this node. So graph.add edge. It is going to, at first we'll start, the first flow is going to be, or the first edge is going to be from start to this particular node here, which is initial. And then after this, I'm going to add another edge from initial to end. So we'll only have one single node for this particular code here. So I'm going to compile this. So to compile, we only need to do port equal to graph.compile and then run this. Okay, so we have some error. I think it's some spelling mistake here. So this should have been initial. Let me run this again. Initial, right? Okay, this is wrong here. So initial. Okay, our graph is compiled. If you want to print this, you can also directly run bot, and then you can see that we have one single node. We begin with the start part, then the process flows through the initial node, and then it goes to the end. So this is our basic graph workflow in LangGraph that we've created. So now, in order to invoke this graph, what we need to do is we simply need to invoke this bot object that we have, and then we need to pass something here. We'll pass messages and then pass our channel name, Learning Hub here. And then we'll print our response. So what happens here is, at first, the initial state in this particular variable contains this string called Learning Hub. Then it moves to greeting node, and then along with that Learning Hub, the state is now updated to this complete message here, and then basically what we get in the end is that particular complete content that we have processed. So if we run this, okay, something is wrong here. So message or messages, let's see, message, state message. Let me just see if I've done any kind of spelling mistakes here. Okay, so this must be message. Okay, so if you see the response, then you can see, okay, why is it only showing just one response here? Having bot, right? Something that I've not done here is return state, because it should return the updated state here. Let me run this again. And then if I run this, so it adds some new text as per the process function or the greeting node function here. And then it gives me the response. So this is a very simple implementation of our graph flow or our workflow using our graph here or using LangGraph. So I hope you understood the concept of LangGraph, and then how it varies from LangChain. In the last two videos, we explored the basics of LangGraph, how nodes represent logical units of work, and how the flow between them creates an AI reasoning pipeline. But until now, our examples worked with simple single message states. In this video, we're taking the next big step, moving towards structured states that carry multiple pieces of information together, just like an agent's memory. So think of state as a data package. It holds everything your graph needs to process, pass, and transform information at each step. We'll start with the code and then I'll try to explain the code accordingly. So let me create a new file here. Complex graph.ipynb. First of all, from typing, import typedict and list. Let me run this and then select the kernel. So it's running from LangGraph.graph import state graph, comma start, comma end. Okay, so these are the imports we'll be needing. So the cell is running. Now I'm going to create a class that contains our state here. So class agent state, and then the type will be typedict. Inside this, I'll have a name, I'll have age, I'll also have skills, and then a result. So, unlike our previous video, instead of just one text, our now states contains multiple attributes like a person's name, age, and skills. After this, we'll be creating our nodes here. So for the first node, we're going to create a function. The parameter will be our agent state. And I'll write a doc string for this. This is the first node. And then here, I'm going to update my state here. So the result variable in the state will be updated. State name, welcome to the system. Then I will return the complete state here. Okay, so this is going to be my first node. Similarly, I'm going to type in the second node now, def second underscore node. Again, it will have a parameter of state. The node will always have the parameter of state, and then it will return the entire state here. Write a doc string. This is the second node. And after this, I'm going to update the state result again here. But first of all, I'm going to bring out my skills and then convert them from a list to a string. Dot join state skills. And finally, I'm going to update my result. So state result plus you have skills in state skills. And then again, I'm going to, or let me just do skills here, not state skills, because I've already extracted my state skills from this. So again, I'm going to pass out the entire state here. Okay. So each node in this particular graph that you see here, or the graph that I'm going to build, reads these structured states and then does its task and then passes it forward, enriching it step by step. So the first node here acts like an initial greeter. It welcomes the person into the system. And then the second node that I have adds more context like the skills that they have. And then I'll also have a third node here. So what is that? Let me write down third node. Will contain an state, agent state again, and then it will return agent state for now. So let me write down, this is the third node. And then here what I'm going to do is I'm going to update my state equals to state result plus, let me add something more here. So in string, you are state age years old, and then end the string here. And then again I'm going to return the state. So the third node completes the flow by including the age, creating a full personalized summary here. So the data flows from one node to another, gradually building the final message, just like a well-organized thought process inside an AI agent. So now we'll build that particular graph. So let me run this. It's running. We'll define a state graph, and then inside it, I'll have agent state. Then I'm going to add my first node. First node will be first underscore node, comma. I will now define the function with that first node. Then I'll also have a second node similarly, and then the third node. Let me copy this down. This is going to be my second node. And then finally, I'll have my third node. So I'm going to add ages now. So first of all, we will go from start to our first node. Then we'll go from first node to second node. Then we'll go from graph.add underscore age, second node to third node, and then finally after third node we'll go to end. Let me compile this. So let me write an object name bot equals to graph.compile, and then print out the bot here or the graph here. So as we can see, it goes from start to first node to second node to third node, and then finally to the end. So the three simple nodes here highlights the true power of LangGraph. It helps you modularize reasoning, breaking large tasks into small, reusable logical units that form a clear and more traceable path of execution. So instead of handling everything in one complex step, LangGraph lets you think and build in stages, exactly like how agents reason in real life. So we'll complete this and then see the result here. So let me build my input state. I'll type out the name here. Name can be Alice. Age and skills can be this one here. So I don't need to pass in the result yet, because that will be formed from within the nodes, and then I'm only going to pass until this skills here. So let me say data science. Okay, then finally what I can do is I can invoke the bot using this input state, and then finally print out my response. So my response will be printed. First of all, what will happen is it will go to this particular node here. So It will take our name and then it will say welcome to the system. With this entire message, it will add you have following skills, and then after that, along with this entire message, it will add the age of the person, and then we'll print the response. So let's see. Skills. Okay, what is it? Skills. What else here? Okay, here I've done some mistake, added an extra space. So let me run this again. And then as you can see, the result is Alice, welcome to the system. You have skills in Python, ML and data science, and you are 30 years old. So based on the flow of data in between these nodes, the result had been updated, or basically some extra strings have been appended in each of these results here. So I hope you understood the code and then understood the concept of this multiple node that we have been implementing here. So far, we built a linear graph that processes structured input and composes a final result step by step, right? But this is just a beginning in LangGraph. In the upcoming video, we'll take this concept further by introducing branching logic, where your graph can make choices dynamically based on the state. In the last video, we learned how data can move from one node to another, with each node performing its task and enriching the overall result. But what if your workflow needs to take different paths depending on certain conditions? That's where things start to get interesting, because in real-world AI systems, not every query or task follows a single linear route. Sometimes your graph needs to choose where to go next, and LangGraph allows that using conditional edges. So in today's video, we're going to see how to introduce choice making inside your graph, how it can intelligently choose between multiple nodes based on logic you define. First of all, we'll write the code and then I'll explain you the code here. So let me create a new file. .conditionalgraph.ipynb. I'll have some imports. First of all, from typing, I'm going to import typedict. Then from langgraph.graph, I'll import state graph, start and end. Let me run this and then select the default interpreter. After that, we're going to write our agent state. So agent state is going to be of type dict, and I'll have number 1, which will be an integer, number 2, which will also be an integer, operation, which will be a float, string, and then I'll have a result, which will also be an integer. Okay, so this will be our agent state here. Let me run this too. Now I'm going to create few nodes here. First of all, the first node will be adder. It will contain state, agent state, and it will also result or return an agent state here. Now here what I'm going to do is I'm going to write a docstring. So this node adds 2 numbers. After this, I'm going to update my final number, or I can sorry, it's not final number, it is result. So state result equals to state number 1 plus state number 2, and then I'm going to return a state here. Okay, then I'm going to define another node here, which is called subtract, and state, agent state. The node will basically subtract 2 numbers, and then what I'm doing here is doing number 1 minus number 2 and then returning the state. Now I will define a router node here which chooses where should I go next. So decide next node. It will also contain an agent state, It will be of type agent state, and then it is simply going to return a string here. So this node will decide or will select the next node of the graph. Now I'm going to check one state called operation here. So if state operation double equals to add, then what I'm going to do is I'm going to return add operation, and then else if state operation is subtract, then I will return subtract top. Okay, so this will be my router node here. So let me run this. Then after this, I'm going to create my final graph. My final graph will be based on state graph, and then it will contain this agent state object. So agent state class. Let me add nodes here. So the first node will be add underscore node, and then the function for this node is adder. Second node is subtract node, and then the function for that is subtract. Then I'm also going to add a third node here. So graph.add underscore node. The third node will be named router, and then what I'm going to do here is I'm going to pass the state as it is here. So it will also be called a pass through function. So whatever we get will just be passed to that router stage here. So now I'm going to go and add edges. So first edge is going to be start, and then it will go to router. Then I'm going to add conditional edge here. So add conditional edge. What will this be based on? So this will be based on the router node, and then what will happen here is its function is this one, decide next node. So the function is here, and then the two options from this node is one is the add op, which will take us to add underscore node, and then the other is the subtract op, which will take us to subtract node. So basically we're referring to add op and subtract op from this particular node here, and then if we get add up, we'll go to add node, which means our adder function, and then if we get subtract up, we'll go to our subtract node, which is our subtract function. Okay, and then what we also need to do is, since both of these add and subtract will show the result and then go to the end of the graph, so what we need to do is we need to add two different edges here, from add to end and then subtract to end. Now since this is done, I'm going to compile my graph. Let me compile my graph, and then if I print out my graph here, we'll see that first of all we'll start from here, then we go to the router node. The router node fixes where we should go next based on the agent state called operation here. If we get plus, then we go to add node. If we get minus, we go to subtract node. From either of these add or subtract node, we go to the end here. So this is how we can introduce conditional graphs in our LangChain. Now I'm going to declare my input state here. So input state is going to be the number one will be 10. Let's say the number one is going to be 10. Okay, I'll keep it 10. Number 2 is going to be 4. I don't need this result here. A result will be operated on its own, and then basically operation is minus. Now if I invoke my bot using input state, and then if I print my final response, then I can see that the result is set. And then since the operation is subtract, so the result is 6. If I change this operation from plus, now the result goes to 14. So either of these two nodes are chosen based on the operation state present in our agent state here. Okay, to summarize now, we start with an agent state that carries our data, 2 numbers, the operation we want to do, and either addition or subtraction. Next, we define 2 nodes, one that adds, one that subtracts. But the real magic is inside this router function here that we have. So this function acts like our choice maker. It inspects the current state and then returns which node the graph should go next. So if the operation is positive, then we go to add node. If the operation is negative, then we go to the subtract node. So LangGraph then uses these conditional edges to make it run. So these edges dynamically connect the flow at runtime based on the conditions, based on the condition functions output. So instead of a single linear chain, what we have here is it is a conditional chain, and it behaves like an intelligent tree, so capable of branching out and adapting to the data it receives. So this concept, conditional routing, is at the heart of making agentic system flexible. So in the upcoming videos, we'll take this concept further, including memory as well as message passing inside LangGraph, so your agents can remember and react contextually, and that is where LangGraph truly starts to feel alive. In the previous video, we learned how to create conditional routes in LangGraph, where our graph intelligently decides which node to visit next based on user input or data state. But what if we want to chain multiple conditional flows together, like a series of choices where one operation leads to another? That's exactly what we're going to explore today. So in this video, we're taking things one step further and see how LangGraph can handle multiple branching routes, letting you create more complex and intelligent workflows that don't just stop after one choice. So we'll first write down the code and then I'll explain you the code here. Okay, so let me create a new file here. 4_complex conditional.ipynb. So first of all, I'll have my code. I'll have my imports here. So the import are going to be from LangGraph.graph import state graph start and end, and from typing I will have type dict. Let me choose the interpreter, and then while this runs, I'll create my agent state. So agent state, this will be have a parameter of type dict. So type dict, I'll have number 1 here, number 1 as integer, number 2 also as an integer, and I'll have number 3 as an integer, number 4 also as an integer. I will have operation 1 as a string, operation 2 also as a string, and then I'll save the result of operation between number 1 and number 2 in result 1, which is going to be an integer, and similarly operation 2 for number 3 and number 4 is going to be saved in result 2, which is also an integer. Okay, so let me run this. So while this is running, now we'll create our functions here. So first of all, we'll have adder, where we'll pass the parameter as agent state. It will again return an agent state. So I'll update state result1 equals to state number 1 plus state number 2, and then I will return the state here. So let me copy this and then create another subtraction operation here. So I will have subtractor2 or sub, okay, I'll write the full function name subtractor2, where I'm going to subtract these two, number 1 and number 2 here. Similarly, I'll have adder2 and subtractor2. So let me just copy this down and then copy it here. So here I'll have adder2, the result will be stored in result2, the numbers are number 3 and number 4. Similarly, in subtractor2 we are going to store the result in result2, where the numbers are number 3 and number 4. Okay, we also need to create two router functions, so let's do that. Choose next node 1, it will have a state of type agent state, and then it will return a string. So if state operation 1 is equal to plus, then what we want to do is we want to return add 1. Else if state operation 2 is equal to minus, then we want to return sub 1. Okay, I'll also create a router for our number 3 and number 4 part here. So choose next node 2. Okay, sorry, this has to be operation 1, and then here we'll have operation 2, add 2, operation 2, sub 2. Okay, so these are our router nodes. Now we'll go on to create our graph here. So graph equals to state graph. I'm not sure why this transition is not being shown, but anyway, agent state, I can just type this. First of all, I'm going to add my first node here. So the first node is adder1, and then I'll give a name adder1 here. Similarly, I have my second node, add underscore node. This is subtractor1. Let me write down the function name here, which is, okay, what did I name it? Okay, subtractor1. Subtractor1. Similarly, I have adder2 and subtractor2, which I'll just create here by copying this. Adder2 and then subtractor2. Now I'm going to add a node for router 1 and router 2, which will basically act as a pass-through function here. So router 1 will pass lambda state and then basically pass the state here. And then similarly in router 2, this should have been a comma. Okay, and then in router 2 will do the same thing. So router 2 lambda state. Okay, now what we'll do is we'll start adding edge. So the first edge is going to be from start to router 1. Then I'll add a conditional edge here. So add conditional edges. Now the detail of this conditional edges is from router 1, it will go to the choose next node 1, and from here we have two options. We can either go to okay, what is the function name? Let's see. So add 1 and sub 1, right? So we can either go to add 1. So if add 1 occurs, then we go to adder 1, and if sub 1 occurs, we go to subtractor 1. Now I'll add one more edge here. So add edge from adder 1 to router 2, and then subtractor 1 to router 2, whichever works in the following case here. Adder 1 and subtractor 1 both should go to router 2 here. Now I'm going to add another conditional edge for router 2 here. So the name is router 2, comma, and after this the function is choose next node 2, and then within this I'll have one more I'll have add 2 which will go to adder 2, and sub 2 which will go to subtract 2. Now after this I'm going to add 2 edges either from adder 2 to end and subtractor 2 to end again. Now this is my final graph. Let me compile this, graph.compile, and then if I print the bot, then we will see our conditional graph here. So from start we'll go to router 1, and then either to add 1 or sub 1 depending upon the operation, and then we'll go to router 2 and then add 2 to sub 2 depending upon the operation that we have. So now what we're going to do is we are going to finally run this using our input state. Let me provide the input state. I'm just going to copy this here. So number 1 is 1, number 2 is 2, the operation is plus. So basically we need to see the result 3 in result 1, and then in case of number 4 and number 7 we need to see the subtraction operation here. So now what I'm going to do is result equal to bot.invoke, and then provide the input state here, and finally we print out the result, and then we can see our result here. So what did we do here? We started by defining an agent state that holds two separate mathematical operations. So each operation has its own pair of numbers and operators, one for each step and then one for the second. Now we define 4 simple nodes here, 2 adders and 2 subtractors. So each of these nodes does the operation and store the result back into the state. But the interesting part here is the 2 routers that we have. So router 1 and router 2. So these routers act like our checkpoints where choices are made. The first router looks at operation 1 and then chooses whether to go to the first adder or the first subtractor, and then similarly for the second router again. So LangGraph handles this beautifully with multiple conditional edges joined together, allowing our graph to branch and rebranch as per needed, just like how complex reasoning systems work in the real world. It's a simple yet powerful demonstration of how LangGraph gives you total control over your workflow's direction without any hard-coded if-else change in your logic. So now instead of having a single choice, your system can make multiple sequential choices, each one based on the updated state of the graph. So this opens the door to designing more intelligent multi-step workflows like multi-turn reasoning, agents, multi-stage data processor, or even complex system that can react to evolving inputs. So far in this LangGraph series, we built conditional and multi-step workflows, graphs that decide where to go based on the data in the state. In this video, we're going to make things a bit more fun and interactive. We'll design a mini number guessing game using LangGraph, where the system makes guesses, checks its progress, and keeps looping intelligently until it gets the right answer or runs out of attempts. This example shows how LangGraph can handle iterations and choice loops, something that's incredibly important when you want your agent to keep reasoning, refining, and trying again, just like humans do when solving a problem. Okay, so without any delay, let's first go into the code. So here I'm going to create a new file to call it number game. Number guess game .ipynb. So from LangGraph, I'm going to import state graph, start and end. From typing, I'll import type dict and list, and we'll also import random here. So let me select the virtual environment. I'm going to create a class called agent state. Agent state. So here I'll have three variables here. The first one will be name, which is going to be a string. The second is going to be a number, which is going to be list of integer. This is basically going to contain the guesses that the model makes, and a counter, which will also be an integer. So at first we'll have a greeting node, which will contain agent state as its parameter, and it will again return an agent state. Let me write down a drop string here. So let me say greeting node, which says hi to a person. So here what I'm going to do is I'm going to update state name to hi there. I have a state name that I'll pass in the input here. So state name. We will start the game. And what I'm going to do is I'm going to set state counter to 0 and then return state. I'll have another state called or another function called random state. This will contain agent state, so this is going to generate number, it will be random between 0 and 10. So state number will be appended with the random number guessed by this model here, 0 to 10. And then I'm going to update the state counter. State counter will be updated by 1, and then I'm going to return state here. The third function will be a router function, which will say should contain an agent state that will return a string. So this will be a function to decide what to do next. Here, if state counter is less than 5, I'm going to enter loop where this will be my state counter value. And I will return loop here, and in the else part, I'm going to exit the loop and I'll return exit here. Now, let me create a graph using the state graph, and inside this, I'm going to pass my agent state. I'll add a node graph.add node. So first of all, we'll have a greet node using greeting node function. Then I'll have a random node. Using random state function. I'll also start adding the edges. So first of all, the first edge will go from start to greet. The second will go from greet to random. And then here we're going to have conditional edges. So add conditional edges. It will start from a random. The function that it should check is should continue. And we'll have two different cases here. The first case, if it's loop, then it should go to random, or if it is exit, then it should go to end. Now I'm going to have one more edge here. If the counter is greater than 5, then I need to end this loop. So one edge will be from random to end. So let me initialize my graph or compile my graph. And if I print my graph, okay, what's wrong? Let's see. So add edge. Okay, add edge edge. Okay, as you can see, so once the model greets the user, then it will enter inside this random node. Then a loop will be carried out if it stays within a certain condition, or else it will exit. Now, what I'm going to do is I'm going to take my input state here. So input state equals to name Abhishek, and the number list will now be empty. And with this, I'm going to invoke my bot with my input data, and I'm going to print my response. So if we run this in loop 1, loop 2, loop 3, loop 4, loop 5, because we've entered a condition for the value less than 5. So in loop 1, it gets 10, in loop 2, it gets 8, 7, 2, and 3, and respectively. So this is how we initialize loop in case of LangGraph. So we'll go to our very beginning of the code, and then we'll see what is happening here. So we start by defining this agent state that holds everything about this game. So it holds the player names, the target number, the last guesses, the total attempts, and the range of the number you can choose from. Then we have three things. We have the setup node. So this basically initializes the state, resetting attempts as well as the guesses. Then we have the guess node here, and then we have the decision node or the router node that we have here. So this is where the power of the LangGraph shines. So instead of using a while loop, we simply create a conditional edge that loops back to the same node until a certain condition is met. So the condition is placed here in this particular part of the code. So each loop iteration updates the state, meaning LangGraph remembers the previous attempts, making the upcoming choices context aware. So essentially, we've not completely implemented the game here, but we've turned this simple guessing game into an autonomous iterative reasoning process, which holds the same mechanism behind how our agentic systems plans, act, and retries while solving complex tasks. And I'm going to end this video for now, but what I want you to do is I also want you to add a target number here, and then basically in this particular router function here, basically check if the model has correctly guessed the number or not. If the model has correctly guessed the number, then the model has won the game. Or if the model has correctly or if the model could not guess the number within the given number of attempts, basically the model has lost the game. So I think you can implement that by yourself. In the last video, we explored the basic structure of LangGraph, where we learned how nodes and edges form the foundation of state-driven AI workflow. We built a simple example that took an input message, processed it through a node, and returned a response. Now, we'll take that idea one step further. In this video, we'll connect our LangGraph with a real AI model, Google's Gemini 2.5 Flash, and see how a complete interaction loop can be created between a user and an intelligent agent. Here, we'll represent our state as a collection of messages, each message capturing the conversation between a human and the AI. The power of LangGraph truly begins to shine here. Instead of hardcoding a linear sequence of actions, like we often did in LangChain, LangGraph lets us visualize and manage the flow of thought, where each step is an independent node that can evolve, connect, or branch dynamically. And by the end of this video, you'll understand how a LangGraph-based chatbot can process user inputs, generate intelligent responses, and maintain conversation flow, all through a graphic structure. This marks our first step towards building intelligent agent, multi-step conversational AI systems using LangGraph. So let's get started and see how easy is it to make your AI think in graphs. So we'll proceed to the code. I'm going to create a new file here. I'll name it AI Agent, agents.ipynb. First of all, start with the import. From typing, I'll import typedict and list. Then from LangGraph.graph, I'll import state graph, start, and end. Then from LangChain_core.messages, I'm going to import human message. Then the model, import chat Google generative AI. Then from .env, I'm going to import load.env. Load the credentials first, and then I'm also going to load the model here. So the model is, as I said earlier, it is Gemini 2.5 Flash model. Okay, so let me run this. I'll select the interpreter and then create an agent state here. So the agent state will be of type dict. I'll have one single messages, which will be a list of human message. Then I'll have a function called process. I'll pass in the state, agent state, and then this will again return agent state here. The response will be invoked from the model here. So whatever is present in the state will be passed to the model, and then I'll get the response here. What I'm also going to do is I'm going to append the same state messages dot append response, and I'll also print this. So AI has passed this response dot content. Let me also add a line break here, and finally let me return state here. Now after this I'll pass state graph, and inside this I'll pass agent state. Let me add a new new node first. So the node name will be process and the function name is process. Let me add two different edges here. So add edge, start to process. Another edge will be from process to end. Process to end. Now compile the graph, and then we can see the workflow of our graph here. Okay, run this agent state, and then we can see our graph here, which goes from start to process and then to end. So basically in the process part, what happens is whatever message is being typed by the user is sent to the model or the AI model, and from there the AI model generates a response. Okay, now what we'll have here is a user input. Let me ask for the user message from the user input. Enter your message, and I'll run a loop until the user types exit. So not equals to exit. And I'm going to print the human message. And then my input state is going to be the messages. Its key will be messages, which will be a list of, or I can do it like this. I can code it under human message. Invoke the bot using our input state, and then basically ask for another user input again. So if I run this, I can pass any message here, hello, and then the model has replied me back. Ask what is your name, and then AI replies back as well. So my each time I enter some text, that will be taken to the model. It will be invoked within our model, and then our model will generate some response here. So this is how we integrate a real world AI into our LangGraph workflow. In our previous video, we saw how to build a simple conversational agent using LangGraph, one that could interact with a real AI model and respond dynamically to human input. But what happens when we want our AI to do more than just talk? What if it could reason, maybe perform calculations, or use specialized tools to find answers? That is exactly what we will do, or what we'll explore in this video. We're introducing the concept of tool nodes in LangGraph, a powerful way to let your AI agent call external functions like the functions you've created and many more. Instead of relying on the model to guess or hallucinate results, we give it direct access to real tools, and LangGraph handles the flow between model calls and tool execution seamlessly. Here, we also use conditional edges, the graph that chooses whether the model should stop or continue based on whether there are tool calls remaining. This introduces intelligent flow control, something that was often more complex to manage in LangChain. By combining the reasoning power of language model with the precision of actual code functions, we're moving closer to a truly capable AI system, ones that can both understand and act. And by the end of this video, you'll see how the model calls the right tools, performs the operation, and keeps reasoning step by step, just like an autonomous agent. And this is where LangGraph begins to bridge the gap between intelligent thinking and practical execution. So, without any delay, let's dive in and see how your AI can now think, plan, and calculate all on its own. So now, let's jump to the code. I'm going to create a new file here. 6_tool_calls.ipynb. First of all, we'll write the imports. From LangChain core messages, we'll have dot messages import. I'll have a base message, and I'll have a system message. Now about the model, this will be my model, and then from LangChain core dot tools, I'll import tool. Then from LangGraph dot graph dot messages, I'll import add messages. Then finally from LangGraph dot prebuilt import tool load. So this should be message, not messages. Now everything is imported. Let's run this. And this is running. First of all, we'll define our model here. Or first of all, we'll load the credential, then define our model as Gemini 2.5 Flash, and then run this. In the next node, I'm going to define my agent state. My agent state will be of type ticked, and then inside this I'll have messages, which will be an annotated sequence of base message, and then in between I'll write add messages function. Okay, now I'm going to create a few tools. In this particular case, we're going to write 4 different functions or 4 different tools for addition, subtraction, multiplication, as well as division. So now we'll create the functions for them. So add the tool def add a integer, b integer. This will also return an integer here. Let me write down the doc string. This will add 2 numbers, then return a plus b. Similarly, we'll do the same for subtraction, but I'm just going to copy this code multiple times: subtraction, multiplication, as well as division. Let me change the function name. This will be sub the 2 numbers, so subtract the 2 numbers. Here we'll have a minus b. This will multiply the 2 numbers. Multiply. Here we'll have a into b, and then this will divide the two numbers, divide, and then A divide by B. Okay, so these will be my tools for this particular system. Now I'm going to list all my tools under this my tools list. So add sub, mult, and div. Now after this, what I'm going to do is I'm going to bind my tools with the LLM. So okay, we have our model. So model dot bind underscore tools. Let's say my tools. Okay. Now we'll create our nodes here. So I write the function for those nodes. So model call will be our first node here, which will have a type agent state, and it will also return agent state. So the system prompt is going to be a system message, and its content will be, you are an AI assistant. Please answer my query to the best of your ability. Okay. Now I will provide the inputs. So inputs will be our system prompt plus the state messages that we have. Then I'll invoke the model with this inputs. Inputs, and then finally I'm going to return messages. So this is going to be state messages plus response. Okay. I will have another router node here, which would say should underscore continue. It will contain agent state as its parameter, and we'll have message equals to state messages. I will pick up the last message from here. So message -1. And then if the last message does not contain any tool calls, then I will take the flow to end or the conversation end, or else I will continue with the conversation, so as to allow the model to call those tools here. Okay, so these are my nodes. Let me run this. Create a graph from state graph. Agent state graph dot add underscore node model underscore call will be represented by model call function. Then here I'll have a tool node object from class tool node, and then it will hold all of my tools from my tools list, and I'm going to add a node called tools using tool node function. Okay, so now I'm going to add edges. So graph dot add edge. The first will be from start to model call. The second will be a conditional edge. It will go from model call to the function should continue. And if the result from should continue is end, then it will end. Or else if it is continue, then it will call tools. So I'll have one more edge here, graph.add edge tools to model call. And I should have one more, I guess, graph.add edge model call to end. Let me compile this and then see the graph. So if you visualize the graph, you can see that we start from here, we go to model call. If it is a tool call, then we go to continue and then call the tool, and again we go to the model call. Or else, if there are no more tool calls involved, then we go to the end. I'm going to create a function here called print_stream. This will contain a stream object. So for S in stream, I will pull up the last message. So if is instance message tuple, then I will print the message, or else message.pretty_print. Okay, now this is going to show the stream of operation that will happen while our tool is being called. So now we'll define our input. So input will be messages, and then it will be from our user, and the message will be add 40 and 12, and then calculate the product with 6. Also tell me a joke at the end. Okay, we'll not do 40 and 12, we'll do maybe 2 and 4, and then the product with 6. And then at last, I'm also asking the model for a joke. So what should happen here is this particular part should be done using our tools, and then for this particular part, the model should call the LLM, and then the LLM should be able to generate the joke without using any tools, because there are no tools present to generate the joke. Now, at last, what I'm going to do here is print stream. So bot.stream stream. Now inside this, I'm going to pass input and then stream node. Sorry, there should be a comma here. So stream node equals to values. Okay, now this brings us to the end of our program. If we run this, we should see a stream of operations that has been happening in order to fulfill our current operation. But I guess we have an error. Let's see what the error is. Okay, I've removed this last part. So let me run it again. Okay, I think I might have found the error here. So what I'm going to do here is node_name, comma node_value equals to next iteration s.items, and inside this I'm going to check if messages is present in node underscore values, and if it is present, then what I'm going to do is so message equals to message minus 1, and then node value equal to node underscore messages minus 1. Sorry, I missed this. Node value. So message minus 1. Let me run this again. What happened here? Okay, extra bracket. So as you can see, our query is taken, and then these first two numbers are taken as 2 and 4 here, and then passed to the add tool. The result is 6. Then both of these 6, and then the following 6 is taken as A and B, and then the multiplication tool is called, and then the product is calculated, and at last the joke is also generated. So this is how we can implement our own tools in case of LLM in LangGraph. In the last video, we explored how LangGraph lets your AI not just think, but act. We saw how to connect tools like addition, subtraction, multiplication, division so that the model could reason, calculate, and decide its own next steps. Now, we're taking that idea even further. In this video, we're building something more practical, a document editing agent powered by LangGraph. We'll call it an email drafter, your intelligent writing assistant that can update, modify, and then save document automatically using AI and tools. But before we jump into the code, we'll try to understand what's happening conceptually. Here, our agent can combine LLM reasoning using Gemini, tool nodes for doing real-world actions, and conditional graph control to keep interacting until the document is saved. We'll define two tools here, update and save. Update to modify the document content dynamically, and save to store the final version into a TXT file. The system prompt that we're going to provide will ensure the AI always knows what the current document state is, and the LangGraph manages when to loop or exit depending on whether the user has saved the document or not. This structure will make your AI truly stateful, capable of handling multiple user interactions over time, and goal-oriented, something that's much harder to achieve in plain LangChain. By the end of this video, you'll see how LangGraph turns your language model into a functional writing agent, one that just doesn't respond, but works with you to create and save real content. So we'll dive in and bring email drafter to life. So I'm going to create a new file here. Call it email drafter.ipynb. Write down the imports. Okay, we'll load the credential first, and then we'll also define our LLM here. Run this. And then we'll have a global variable. To store document content. So we'll write document content equals to an empty string. Now we'll have our agent state class. Any other messages will be of type annotated, sequence, base message, and then add messages. Now, as I said, I'm going to define two different tools here. So the first tool will be update. We'll have a string content inside this, and then we'll also return a string content here. So I'll write down the doc string. Sorry for this. So this is going to update the document with the provided content. Update. Okay, so I'll access the global document content here. Then what I'm going to do is document content equal to the content that I get here, and then I'm going to return a string here which says document has been updated successfully. The current content is document content. Okay, so this is my first function or my first tool function that I have. Next, I'm going to create another tool called save, where I'll provide a file name in string format, and then I will return a string here. Write down the doc string, save the current document to a text file, and finish the process. The arguments that I'll be passing here is the file name, so which will indicate the name of the text file. Also, again, I'm going to access the global document content. Then if there is no file name created, then I will provide a file name.txt file here. Then I'll try to open this file. As file, and I'll try to write the document content into this file, and then print document saved successfully as file name, and then also return the same. If we have an exception, then I'm going to return an error message here. Okay, so these are my two tools that I'll be using. Finally, I'll create a list of my available tools. So the first one is update, and then the second one is save. I am going to bind my tools, bind the LLM using my tools. So my tools, and then I'm going to create a tool node object using my tools here. Okay, now I need to define my nodes. So our first node is going to be our agent. It will contain agent state type. It will also return an agent state. So what I'm going to do here is I'm going to provide a system prompt. Let me just copy this prompt from somewhere. System. Okay, I'll just copy this entire thing from somewhere so that you can pause the video and then see what the actual prompt is. Okay, so the prompt is you are an email drafter a helpful writing assistant. You're going to help the user update and modify document. If the user want to update or modify content, use the update tool. And then if the user want to save and finish, use the save tool. Okay, so this is done. The current document content is also passed here. After this, what I'm going to do is I'm going to check if user message is not provided. And based on this, I am ready to help you update a document. What would you like to create? Okay, this is the first message that the user will be seeing. And then I am going to encode this inside human message, or else if there is already some content that has been generated, then the user input is going to be, so this should be an input. What would you like to do with this document? Then I will print user and then print the user input. Then put it inside the user message again. Okay, now these two states are done. What I'm going to do is I'm going to combine the system prompt as well as the user message that we have. So this will go inside all messages. It will have system prompt plus list of state messages plus user message. Now I'm going to invoke the model response equal to model.invoke. Invoke using all messages. Sorry, it's model here. Okay, then I'm going to print out AI response here. Or just write down AI. And then print out response.content. Now I'm going to check if there is any tool calls provided in this particular response. So if has ttr response tool calls and response dot, sorry for the autocomplete part, response dot tool underscore calls, then I will print which tool is being used right now. So invoking tool, please be careful with the brackets here. So tc tool name or tc in response.tool calls, and then I'm going to return the messages, which will be the list of state messages plus user message as well as the response. Again, I think I missed a bracket here. Okay, this one extra bracket is extra. Okay, so this is done. So this is for our agent node here. Now I'm going to create a router node. So router node will be shared. Continue. It will contain agent state, and then it will return a string. So the doc string for this determine if we should continue or end the conversation. Okay, so first of all, access our state messages. And then if there is nothing, then we should continue, or else if there is something inside this, then we reverse the list and then check the instance and see if it is save or like if the tool call name is present is in the form of save. So is instance message, it is message, right? Okay, so message and then tool message. The spelling is wrong here, so for each instance message and then tool message and saved in message.content.lower. Still this is not complete. And document in message.content.lower, then we return end, or else we return continue. Okay, so our router node is also fixed. So what we're basically saying is if we don't have anything, then we should continue. If we have save, then we should end the flow, or else if we don't have save or like if we have update, then again we should continue the flow. Okay, so this is done. Save this, call our state graph, add a node, this will point to our agent, add another node, I'll have tools. Now I'll start adding edges. So from start we go to agent, and then from agent we go to tools, and after this I'm going to add conditional edges here. We'll start from tools, we'll go to should continue function, and then from should continue function we have two options. If we have continue, we go to agent. If we have end, then we end our flow. So let me compile this graph.compile, and then print out our state graph here. So as you can see, we start from here, we go to agent, we go to tools. If we have to keep on updating our document, then we continue this particular loop here from agent to tools, and then tools to agent. And then once we call the save tool, then we go to the end of the conversation. Okay, now I'm going to create some function for prints. So print underscore messages, it will contain our messages. Inside this, function made to print the messages in more readable format. Okay, so if not messages, we just return. If nothing is there, we just return empty. But if we have messages, and then we specially focus on the last 3 messages that we have, then what I'm going to do is I'm going to check if instance message is a tool message. Then I'm going to print out tool message result.content. Now to run the document agent, I'll create a new function. So at first, the state is going to be messages and then empty message. Then let me run this. So first step in bot.stream state, if messages in step, then print messages, step messages, and then it's done. And then at last, we can print out conversation ended. Okay, so let me run this. And then finally call run document agent. Now if we run this, so what it asks me is, I'm ready to help you update a document. What would you like to create? So write me a leave requesting email for 22nd October, sorry for the spelling, October 2025. Write me an email. Okay, the AI says, what should the email say? It should be about leave application. So the AI agent does write me an email. Now I want to replace the start date, replace start date to 22nd October and end date to 23rd October 2025. Let me save this file directly. Or I can say the email should include my name as Abhi, and then it does replace my name here as Abhi. So everything is done. What I need to do is I need to save this file. So if I say save the file now, save it. So it asks me for a file name. So I can say email draft, and then if we see somewhere in our folder location, then we see that we have an email draft file where the AI generated content is saved here. So this is all about the email drafter application. I've made a few changes here in this particular part here, as well as in this particular cell here. So please go through the changes and then I hope it runs on your end as well. So in this video, we've seen how we can use LangGraph as well as our real world AI model to invoke the tools that we have and then do something meaningful for us. In this video, we'll see how we can build our RAG agent using LangGraph. So let's start our video by creating a new file, 8_RAG agent.ipynb. Well, for this RAG agent, I'm going to use a file. I have a PDF file that I'll be using. So let me paste that file here first. So this is a stock.pdf file. I'll be using the data from this particular file for this RAG agent here. Okay, so now first of all, start with imports. Import type dict, annotated, and sequence. Now from LangChain core, I'm going to import something called human messages, tool messages, system message, and base message. So import human message. I don't need AI message. I'll need a tool message and a base message and a system message. From operator, import add as add_messages. Then I'll open the model or import the model, import Chat Google Generative AI as well as the Google Generative AI embeddings. Then from LangChain community, I'll import PyPDF-loader to open the PDF file. PyPDF-loader. Then we'll import recursive character text splitter, LangChain.textSplitter, import recursive character text splitter. Then for the vector database, I'm going to use Chroma, import Chroma. And finally, for the tool part from LangChain_core, I'm going to import tool. Load the credential first. Then I'll load my model here. The model will not be Gemini Pro. I'll remove the temperature for now, but it is going to be Gemini 2.5 Flash model. And for the embedding model, I'll be using so model equals to model/Gemini embedding 001. Okay, let me run this. First cell, and the cell is running. Okay, there is some error here. Let me see what the error is. So Gemini 2.5 Flash should be correct. Okay, it should not be model name, but it should be model. Let me run it again. Okay, the model is imported. I'm going to copy this, not put it here, but put the PDF file inside this LangGraph folder so that it can be easily accessed by the notebook file present in this folder. So PDF path equals to stock.pdf. So this is going to be my PDF path. And then we'll try to load the file first. So for that, what I'm going to do is I'm going to check if the file exists or not. Path.exist PDF path, but like if it does exist, then I'm going to do PDF loader equals to PyPDF loader PDF path. Okay, this is also running. Now I'm going to load the pages from the PDF path. So load the pages from the PDF. So I'll put it inside our try block PDF loader.load. Let's also print something. So a PDF has been loaded and has a certain number of pages. If it cannot be loaded, then we'll load an exception and then print out our exception here. An error occurred while loading PDF, and then simply raise an exception. So our PDF has been loaded and then it contains 9 pages. Now what we're going to do is we are going to use our splitter here. So text splitter equals to recursive character text splitter. The chunk size is going to be 1000 and then the chunk overlap is going to be 200. That's okay. I'll keep that for now, but you can change the values according to your need. If you want to make smaller chunks, more smaller chunks, then you please reduce the chunk size. And then if you want to overlap some information between chunks, then you increase the value of this chunk overlap. So now let me split the pages. So pages underscore split equals to text splitter dot split document pages. So if we want to see total number of chunks, then we can print it out, and then we can see that we have now divided it into 24 chunks. If we reduce this chunk size to maybe 500, then we should see that the chunk that our chunks are, or the total chunks number should be increased here. So if we keep it to 500, then we go to 60 chunks, but right now I'll keep it to 1000 and then we have 24 chunks. Okay, now we go to our vector database part. So for vector database, I'm going to give a collection name. So collection name is going to be stock market. So we'll try to create a vector store from this one. So vector store equals to Chroma.from documents. So document equal to pages split. For embeddings, I'm going to use my embedding model, and then for collection name, I'm going to use my collection name. And then finally, we're going to see our success message here. But if we run into any kind of exception, then we'll print an exception and then raise some error. So if we run this, it will take some time to be vectorized, but our vector store has been successfully created, means that try block has been executed successfully. Okay, now we'll define our retriever part. So for retriever, we'll do vector store dot as retriever, and we'll define our search type. Search type will be based on similarity, and then the search keyword arguments will be we'll keep it for 3 for now. So the retriever part is also executed. Now we define our tool. This tool will be our retriever tool. It will contain a query of the form string, and then it will again return a string here. Provide a doc string for this. So this tool searches and returns information from the stock market performance report. document. Okay. We're going to invoke our retriever using our query. So retriever dot invoke query. So if nothing is found with similarity to query in our document, then we print out or we return no relevant information found. Or if something is found, then we are going to embed this in a list. So for iDoc in enumerate documents. So I'm going to append everything inside this results list here. And then what I'm going to do is I'm going to convert this list in string form. Now we only have one tool which I will wrap inside this list. Then I'm going to bind my LLM using this tool with the help of the function bind tool, and then run this. Now we'll have our class agent state. It will be of type dict. I'll have messages, which will be an annotated sequence of base message, and then here what we want to do is we want to keep adding our messages. So I'm going to use this add messages function. And then I will define a router function, should continue state agent state. This will return the tool calls if it has. So what it is going to do is check if the last message contains tool calls. So for that, I'm going to see my last message, and then I'm going to return the result tool calls, and len tool calls is greater than 0. Okay, so this is also done. Now what I'm going to do is I'm going to write a system prompt, which I'm going to copy from my source. So this is my system prompt. You are an intelligent AI assistant who answers questions about the stock market performance in 2024 based on the PDF document loaded into knowledge base. Use the retriever tool available to answer questions about the stock performance data. You can make multiple calls if needed. If you need to look up some information before asking a follow-up question, you're allowed to do that. Please always cite the specific parts of the document you use in our answers. So now what I'm going to do next is run this, and then I'm going to create a tool state, and then here I'm going to do our tool dot name, our tool for our tool in tool. So it should be tool, right? Yeah, in tool. Run this again. So this is also running. Now we'll define our LLM agent. So def call LLM. It will contain agent state. It will also return agent state. Agent state object. So function to call the LLM with the current state. So here what I'm going to do is I'm going to make a list of my messages. So list of state messages. Then I'm going to convert this into a system message, or I'm going to append my system prompt as well as the messages that we have. And finally, we're going to invoke our LLM using the combined message that we have. Okay, so this is done. I don't think I need to mention this messages. So I can just do message here. And then what I'm going to do is I'm going to return message, messages, list of message. Okay. This is also running. Now we create one more function for our retriever agent. So def take underscore action state agent state. It will also return agent state object. So what this function will do is this function to execute tools from the LLM's response. So for this, what I'm going to do is I'm going to check if we contain any tool calls from the LLM. So tool calls equals to system message -1 for tool calls. If there is, then we'll append everything inside results. So now we'll loop through our tool calls. So we'll try to understand what tool is being called here. So print f executing tool name with certain input. So if not the name interdict, I'll do tool not found. Or I can just keep it inside the result, but it's okay. I can keep it like this for now, but I don't want to directly append this. So what I'm going to do here is I'm going to do a result equals to tool not found, else I'm going to append this inside the results using the tool name. So tname dot invoke dargs dot get query, then print tool result here. Then what I'm going to do is I'm going to append the tool message that we get from the above loop. So here results dot append tool message. So tool call id equals to t eid, what else, name equals to tname, and content equals to str result. This should be inside the for loop, sorry. And finally, I'm going to print tools executed, and then return the agent state response. Okay, now we build our graph using state graph, agent state. Add our first node, graph.add node, which will be our add node, which will be LLM represented by call LLM function. Then the second node will be add node. The second node will be retriever agent. which will be represented by take action function. And then the first edge will be graph dot add edge. Add edge, it will go from start. I've not imported start, I guess. So let me also import start. So the first node will be from start to LLM. Then what I'll do is I'll add a conditional edge. Add conditional edge. This will go from LLM to should continue. And then we'll have two different cases here. For true, we'll go to retriever agent. And then if false, we'll go to end. I'll add one more edge here from retriever agent to LLM, and then the entry point will be from LLM itself. Okay, what's wrong with should continue? Let's see. Okay, the spelling is wrong here. Should underscore continue. Something's wrong here now. Function is not callable. Okay, let's rerun everything from the beginning. So this is running, tool collection is running, this is also running. The tool call is also running. Now the graph is also built. Let me compile the graph. Call it rag agent equal to graph.compile. And then if we print out our rag agent, then we should see our flow here. So from start, we go to LLM. If it has tool calls, then we go to retriever agent, then we go back to LLM. If it has multiple tool calls, we again reciprocate through these retriever agents. And then once our LLM call is complete, then we go to false and then end the conversation. So finally, we'll define a function for running our agents. So def running agent. So we'll use a continuous loop here, and then we'll ask the user for their question. Input what is your question? So if the user input is exit or quit, then we exit the agent, or else we're going to append the user given text into a human message. Then we will invoke our rag agent. Then we'll print the agent response here. Okay, so this is also done. And finally, we'll call this running agent function. Since it was a long code, I hope we don't have any errors here, so we can run the application. Okay, so initially this is being run now. Okay, what do we ask here? So we'll ask what is the document about. Okay, we have an error. Let's see what the error is. I think I found my error here. So this should be inside a list. The system message should be inside a list here. Because if we don't keep it inside the list, then this is not considered as a base message. Let me read on everything again. Okay, so what is the document about? we still have an error. Let me check again. For this one, I'm also going to edit my retriever agent function. So let me rerun this again and then see if I get an error. So what is the document about? Let's see if we get an error. Okay, so the query is gone, and then we have two different sources from where we're getting result, and then the agent responses. The document is about stock market performance in 2024, specifically focusing on something. Okay, now we'll open this stock market document and then see what this document actually contains. What happened here? Okay, so let me rerun this again and then check. Meanwhile, I'm going to open this document. Okay, so this is our stock market document. It contains some data, and I will be asking question based on this here. So rerun everything again and then see if we can continuously talk to it or not, because I think we're getting some error there. We'll also fix that. Tell me about the EV leaders. Who is the electric vehicle leaders in the market? It should find that the EV leader vehicles are this company here. So the agent response is correctly given, and then we'll ask how much did they gain. So how much did Tesla gain in 2024? So from late 2023 to 2024 gains are occurring in there. So it contains a lot of content here. So it does give me the share price and then the growth as well as the sources as I asked earlier. So yeah, let me go to something else and then ask it. What was S&P's gain? So it should give me that S&P's gain was 25%. Okay, so this is working quite well. So this is how we implement RAG using our LangGraph. Okay, I'll ask it something that is not present in the document, and then we'll see what it tells us. So why does the sun rises in the east and sets in the west? So it should not have any response for this. So it says, I cannot answer this question using the provided document as it was stock market performance and not astronomy. So this is working quite well. I'm going to end the video here. So I hope it implements on your end too. Be careful about the content of this particular function here, because there are too many brackets being involved here. So you might make some error. If you have any questions, feel free to comment down below and I'll try to help you out. And I'll see you in the next video again. Let me exit the system, and then it gracefully exits again.